each other, right? Oh, kau tak tahu kan? Tak. They like to kiss under mistletoe. They have that plants hanging, then dia buatlah benda nak buat. Okay, kejutan budaya. Go back. Sebab very few parasitic plants. Most plants are photosynthesizing. Anyway, so you have a piece of leaf like this, like a leaf like this. Yep. What plant is this? Kau apa ni? Kau getah? Ya, getah. Ya, what getah ni? I think nama dia, cuba Google happy bean. Betul tak nama itu? Or maybe not so happy. Rasa pokok happy bean ni. Rasa. Yeah. So you have a leaf. This is the regular cross section of the leaf. The upper side of the leaf, this upper side, and then the underside of the leaf. So regular leaf like this, usually the underside having lots of pores for gas exchange. Okay, these pores, these microscopic pores are called stomata. Very important. So to do photosynthesis, the plants require ingredients because it is a process. So what are the ingredients of photosynthesis? Water, light, carbon dioxide, and some nutrients. Okay, the basic ingredient for photosynthesis. So for the light, that's pretty much the same. For the light, you have the leaf. So the leaf, the topmost layer of a leaf cross section, the epidermis here, these cells are actually transparent. That's why the light, the sunshine, can pass through the leaf and then illuminate the entirety of the cell tissue in the leaf. Okay. A bit of difficulty when it comes to the second ingredient for photosynthesis, namely carbon dioxide, the CO2. You see, there's CO2 from the outside here. So this is another view of the cross-section leaf. CO2 from the environment here, before even it reaches the leaf, it has to go through so many resistances. Look at the symbol here. This is the symbol of resistor that you learn in school, right? The small thing. CO2 has to grow so many resistance before it can reach to the photosynthesizing cell. In plants, there are many cells, even for a given leaf. However, not all cells do photosynthesis. Cells that do photosynthesis we call mesophyll cells. Okay, two types of mesophyll cells usually. The palisade mesophyll cells that looks like a column here, and then spongy mesophyll cells that are more spacious from each other. Right. The journey of CO2 from the outside here, our environment, to get into the plant and then to reach the photosynthesizing cell is very not straightforward. Okay. First, it has to change the CO2 from the gaseous state. The moment it gets into here, it has to change into the liquid phase. Right. Yeah. Then it has to go through all this invisible barrier that is called the boundary layer here, and then to pass through the membranes and also the plant cell wall. So there are many gates that it needs to pass through, right? So plants have engineered itself so that it is more conducting to this second ingredient of photosynthesis, namely CO2, right? For example, the epidermis of the plant has been engineered to become transparent, so the light can pass through. But for the CO2, the plant has engineered certain structure. For example, the stomata can control the opening, close and open as the plant needs, and also the arrangement of the mesophyll cells close to each other to facilitate gas movement. Right? Okay. All so that eventually the CO2 can reach inside the cell to reach chloroplast, because chloroplast is the place photosynthesis takes place. Okay, right? So this is the cross section of a chloroplast. Why is it important? This is not just to bombard or to scare you with anything. This is just to tell you, you need to understand where exactly this machine is measuring. What exactly is it measuring? Because photosynthesis is not a single process. There are a number of things that are happening at once at different locations within this small structure. This is super small, okay? About maybe 1 micron or maybe less, super small. You know how small is 1 micron? What's the smallest unit for this? 1 mm. 1 micron is 1000 mm. So it's super small, right? So this is a cross section of a regular chloroplast. So the important things you need to understand: two places. This stacking of pancake here, we call it grana. That's plural. Singular for that is granum. Each individual pancake is called thylakoid membrane. Okay, this thylakoid, that's the spelling. The first part of photosynthesis happens there, in the membrane of the thylakoid. This, yeah. The environment inside the chloroplast, which is this region here, I would like to call it as the chloroplast porch. You know, the yard of the chloroplast. This is where the second part of the photosynthesis happens, and this region is called the stroma. Yeah, that's the word, stroma. So two locations important in chloroplast: the thylakoid membrane, this green pancake, and also the outer environment, the stroma. Bear that in mind, okay? Because we're going to see that a lot in a bit. Go on. Yeah. Look at the name of photosynthesis. Photosynthesis, meaning that it is not a single reaction. Photosynthesis, you can divide it into two separate biochemical reactions, namely the photoreactions and also the synthesis reactions. Photoreactions is also known as the light-dependent reactions in many textbooks. Okay, and this happens in the thylakoid, the green pancake, this part. Okay, the photoreaction or the light-dependent reaction, just a synonym. The second part of the photosynthesis is the synthesis part, or known popularly as the Calvin cycle. Happening where? In the stroma, okay, the porch or the foyer of the chloroplast, right? So these two are interconnected somehow. By interconnected, I mean the product of one reaction is used by the other reaction to complete the goal of photosynthesis, which is producing sugar. Okay. Even that is still an oversimplification. Photosynthesis actually do not produce direct sugar. What photosynthesis produces is actually sugar precursor, the building block for sugar, right? Yeah. Okay, go on. Yeah. Remember this? You come in again. How many? One more? I forgot to tell. Some of you might learn chemistry, still remember chemistry, right? This number 6.02 times 10 to the power of 23 is called Avogadro's constant. Or number like chemistry a lot? Do you have a chemist here? So should know this kind of stuff, right? Okay, so coming back to the first, so we look at now the first reaction of photosynthesis, which is the photoreaction. Two things important now, which is the light quantity and the light quality. Okay, the light quantity is how many particles being absorbed by the leaf. Particles of what? Particles of light. Light particles, the name is photon. Photon, light particle, okay? Photon, light particle. Bukan proton. Photon, anybody got X90? Tak keluar lagi. Dah buat review. Okay. And the second thing is the light quality, which is the color that coming to the leaf. Okay, right, go on. Now I want you to remember the green pancake, the thylakoid membrane. Zoom it all the way to the surface. Then take the knife, slice it open. Then you get this. Should be green actually, but it looks purple, maybe it's scared. Slice, this is the slice of thylakoid membrane. Okay, see the outer side, the inner side of the thylakoid membrane. The outer side is the stroma. The inner of the thylakoid membrane is the lumen. Okay, right. So zoom even further into the membrane of the thylakoid. You have these busy looking reactions of light happening. Okay, what is this actually? Is actually, remember again, this diagram that you saw earlier. So what exactly happened? Sunlight, doesn't have to be sunlight, any source of light coming towards the leaf, travel and then hits the leaf. The leaf is transparent, remember? The epidermis is transparent. The light, it will eventually hit many pigments that are present on the surface of the thylakoid membrane. Thylakoid membrane, even though in the depiction it usually looks green, but green is not the only color that is present in the leaf. You see it's green, right? Do not think green is the only color. If you run with liquid chromatography, you're going to see there are many colors in here. Yellow, red, purple, blue, gray, all sorts of heavens in there. Yeah. So why is it important? There is one special chlorophyll molecule that is going to do the entire photochemistry. This special chlorophyll A molecule, we call it the reaction center. So for a given thylakoid membrane, there are many chlorophyll A molecules. A system like this. This is only one system of photosystem 2 and photosystem 1. So if you imagine this is like a complex of photosystem. On a thylakoid membrane, maybe there are millions of these scattered throughout the surface of the thylakoid membrane. So the light comes in and then it hits various pigments that are present on the leaf. Remember, light from the sun comes in various wavelengths. Okay, sometimes it comes in the right wavelength that can straight go to do the photosynthesis. But most of the time, the wavelength is not correct. It's just too much energy, right? So the energy that comes into the leaf will be first absorbed by the various pigments in the leaf so that the energy can be reduced to the correct wavelength, right? So what is the wavelength that the plants need to achieve? This is the number, 680. For example, the sun that you see here, the moment it hits the molecule here, maybe the energy is 400 because it's blue light. Is that the correct one? No. So it passed to the second molecule. The moment it passed to the second molecule, 400 nanometer will become 420 nanometer. It becomes less. So one thing you need to understand about light, it kind of go against your regular understanding. I can make a quick. Jauhnya lah. So let me take side of it. Ada sound effect ni. Okay. High. Ini maksudnya wavelength, okay? Lambda ni. Wavelength. Lambda is the universal symbol for wavelength. High lambda in the unit of nanometer equals to low energy. Low lambda, high energy. So it kind of terbalik, opposite. Okay. So coming back to here, the first light, let's say that arrived here in the form of 400 nanometer, when it passed to the second molecule, the energy is reduced. When the energy is reduced, the lambda is going to increase in number. Okay, so maybe in here 420 nanometers. Not correct. It will pass to the second molecule, maybe 450, 500 nanometers, 550, 460, all the way until it reaches 680 nanometers. Keep on passing. Every time it's passing, the energy is reduced. The kind of like the example, if you learn from the school, remember from the school, the special device that the science teacher used is called the tuning fork. You know tuning fork? I know the Malay name for it. What's the Malay name for it? Tala bunyi. You bang it against the cable, benda tu gagal kan? Then you touch one pond of water. The water going to cause big ripple. What's ripple in Malay? Ripple lah. Sempang. There's a word, I forgot. Hari tu dah jumpa dah because orang tak faham ripple tu apa. Gelombang air, riak air, ya. Riak air. Bukan riak abo tu. Bukan itu. So you touch one part of water, you're going to get a very violent water ripple. Then the same tune fork, you touch the second point, the ripple is going to be calmer than the first one. Because the energy has been reduced with the movement of the tuning fork. Kind of like this. Yeah, the concept is similar. Moving, get reduced energy. All the way until 680 nanometers. So what happened here? So this chlorophyll A molecule has a loose electron. Okay? And this electron can be ejected out. It can literally get out. Who can get it out? Only one energy can get it out. 680 nanometer worth of energy can only click, put it out. Right? The moment it is out, it becomes excited, of course. It will be passed to various molecules embedded in the thallic membrane known as electron acceptors. There are many electron acceptors here, starting with the pheophytin. Q stands for quinones, quinones A, quinone B, plastoquinone, cytochrome B6F, that's the short form of it, plastocyanine, and then eventually come to the another photosystem, the photosystem 1, okay? And then this molecule will get ejected as well, but notice the number is different now. The photosystem 1 requires slightly lower energy to get activated. Okay, so when this chlorophyll P700 gets activated, it will do its own electron transport change, just like this one, but eventually it will reduce a molecule forming this thing called NADPH. Okay, I know up to this, many people start to kimia. Relax. This whole purpose of doing light reaction is to get two things. Two primary product, one byproduct from these whole reactions. Okay, so the primary product dapat untuk light reaction or photo reaction. Number one, you need NADPH. Or the easy word to know this guy does what is electron donor or reducing agent if you learn chemistry. The second thing that you get from this reaction is ATP. Okay. What about the byproduct? The byproduct for this, you get oxygen. Oxygen. Where do you get oxygen from here? You see when the electron got ejected out from that special chlorophyll molecule, that chlorophyll now has a hole in its tummy. You can see through. Perut dia berlubang. That needs to be plugged in. Di-plug in apa? It will steal electron from the nearby water. The moment it steals electron from the water, water will split. The H2O will split. This event is called photolysis. When photolysis happens, you will release oxygen. That's how you get oxygen. And you use this to breathe in. Okay? The byproduct for the plant, used for other organisms on the planet to breathe in. Okay? And then eventually you will also get ATP, but I'm not going to go too much into that. Just know that two products that you get, and NADPH and ATP. So ATP is actually the energy currency, or phosphorylator. Phosphorylator. Meaning that it can donate as well. It donates phosphate. NADPH, nicotinamide, adenine, dinucleotide. H means reduced. Reduced means it has extra electrons to it. Whose electron? Hydrogen. Since it is extra, it can donate. So whoever receives it will become a new molecule, and this thing will revert back to NAD. Right? Okay. Right. Go on. Yeah. So this is the summary for the first reaction of it. You get NADPH, ATP, adenosine, triphosphate, and oxygen. Oxygen will go out. The plant can use its own oxygen byproduct, but sometimes it just do not use that much. Most of it actually being consumed by us. Did you know that most of the oxygen from the planet do not come from the plants? Where it came from? Apa? Kilang? Yeah, from the ocean, from the kelp, seaweed. Yeah, about 70% of the oxygen from our planet came from the sea or from the ocean. You cannot see the sea. No, I need to. You cannot see the seaweed in the ocean. There is a whole bunch of forests under the ocean. Keep on producing oxygen throughout the day, because the ocean got kind of like spinning, right? So the sunlight illuminating the whole ocean. So you can imagine berapa banyak CO2 oxygen yang keluar. Yeah. Okay. So we're done with that. So this product now is very important. This will be used to feed the cycle in the second part of the photosynthesis, which is the light dependent or Kelvin cycle. Go on. Yeah. So this is a cycle. Remember, this is not happening anymore in the LiCOR membrane. You are in the different location now. We move to the second location, which is the stroma, outside the LiCOR membrane. So in the stroma, there's always present some amount of sugar, precursor sugar, in order to make glucose that you always know about. So Kelvin cycle itself comprises three phases: carbon fixation, carbon reduction, and carbon regeneration. Three phases. The CO2 that has managed to enter the chloroplast will now combine with a 5-carbon sugar that is already present in the cell with the help of special enzyme called Rubisco to be fixed into 6 molecules, which is unstable. Then it will immediately be broken down into 2 molecules known as 3-phosphoglycerate. This phosphoglycerate molecule will be reduced by the help of NADPH, meaning that the electron now is absorbed into this phosphoglycerate molecule. Okay. There are many steps between here and here. The changes here requires ATP. This is why you need the ATP to change the CO2 that has been fused with 5-carbon sugar into phosphoglycerate. That requires energy. Phosphoglycerate will be changed into this molecule G3P, which is glyceraldehyde 3-phosphate, and that requires the action of NADPH. And then the cycle actually continue doing a lot of stuff, but we just exit here. One exit from this stage, you get half a glucose. Glyceraldehyde is actually half a glucose. 2 times of that, you get 1 glucose, right? So this is why I said earlier, photosynthesis is actually making the sugar precursor. This is the sugar precursor here. Yeah. And then the cycle will continue also on, so that the whole event doesn't stop. Talking about this machine, so you have understood the photosynthesis have 2 reactions now, first reaction and second reaction. Can you go back 1 slide? Yeah, going back here, right? Or maybe the after side already got this. Sometimes I would like to put 2. No, go down, go further. Oh no, go back. Go back. So this photosynthesis machine exactly is measuring what? If you say that, oh, that looks complicated, this is photosynthesis. This is also photosynthesis, right? 2 biochemical reaction. So this guy measuring what? Exactly. Is it measuring how many sunlight get absorbed in here? Or is it measuring how fast this cycle going? So this machine got various spec. The one that you have, I think you also have the high spec, right? Yeah. They got 2 modes: the gas exchange mode and also the fluorometry mode. Okay. For the gas exchange mode, which you use it for most of the time, it actually measures. Go back 1 slide. The first phase of Kelvin cycle. Go lagi. No, ke depan lah. It's fixing. It's measuring the first part of the Kelvin cycle, the carbon fixation. So this is what this machine does. It's not measuring how much reduction happening or how much reduction going. No. It's measuring for 1 second for a given known area, how much carbon dioxide is assimilated or fixed into the plant. This is what this machine measures. Okay? And that is regularly known as the assimilation rate or the net photosynthesis rate, sometimes people call it. Okay? Just because people call it photosynthesis doesn't mean that it's measuring the whole story. No, it's measuring very specific, that part only. What about the other part of it? Go back one slide. One slide. What about this? This machine can also measure this as well, but you need to change the mode into fluorometry mode. Okay, gas exchange doesn't measure this. Okay, so with the fluorescence, we're going to see fluorescence. Oh, tomorrow we're going to see this tomorrow. Apa dia gerak-gerak sangat ni? Okay. The fluorometry mode of it will measure the health of the photosystem and also the fluorescence of the chlorophyll A in the thylakoid membrane. Okay, you can do one individually or you can do both at the same time, but there is a way to do it, right? Okay, so if you have it, then your photosynthesis story kind of complete. Right? Okay, go further, go further, go further. All right. So this is the gas exchange mode that I was talking about. So what kind of data that you get? So you can get data like assimilation. You can get the Rubisco kinetics. Rubisco is the enzyme that do the CO2 fixation. The speed of it, or maybe you want to study the electron transfer rate. That is possible as well under the gas exchange mode. Right? We call it this type of measurement as the steady state measurement or the survey measurement. It's very quick. You just open it, clamp it, then log data. So maybe in 1 hour, you can get reading of 20 plants. That's why it's called survey measurement. Quickly understand the rate of carbon fixation for the leaf. Right? Go on. The second mode, which is the fluorescence mode, this is a bit complicated. This tomorrow, I'm not going to teach too much about it because people who learn this, let's just say I have not met anybody who can remember it 3 times learning this. Even dah learn 10 kali pun still tak boleh nak ingat, tak tahu kenapa. Maybe because this is actually physics. Okay. In essence, fluorescence measuring the properties of the leaf that glows in the dark. Simply put, you see, leaf absorbing light, right? Not all light is used for photosynthesis. Some light is actually released back. This released back is actually the invisible glow in the dark that you cannot see, but this machine can see. Alright, so the machine can see. It will be detected with the sensor in here. So you quantify that fluorescence. Okay. So with that, you can understand the maximum capacity of light capture by the plant and also the health of the photosystem. What does it do with the light? Does it do photosynthesis or does it just throw outside to the window? Okay. This can give a good decision whether you want to increase nitrogen or not. If your plants are not doing so well with the photosystem efficiency and so on, maybe it's about time to give a bit more nitrogen. Yeah, to increase the chlorophyll production and so on. Yeah, right. Okay, next. Yeah. And finally, in addition to the gas exchange mode survey measurement, fluorescence measurement, this piece of equipment also able to generate response curve. Okay, so response curve, you need to change the mode again in here. It's called the auto program. So auto program here, you can set the machine to measure at various amount. For example, in light here, from 0 to 1000 with the interval maybe 100, 100, 200, 300, 400 micromole of light, and then you see the effects that it has on the assimilation rate in here. Then you can produce something like this, the light curve, the light response curve. You can change anything on the x-axis here, anything that you want. Degree as high as 10 degree, right? But it's a lot easier to go higher than to go lower, right? Might put that into mind. Or you just want to play around with the CO2. You want to understand how the plant is going to respond to low CO2 concentration or high CO2 concentration. Yeah. In physiology, all of these response curve activity give beneficial information actually. For example, that like the light curve, it tells you whether the plant is a shade plant or a sun plant. You know the concept of sun shade plants? Yeah. So with the light response curve, we can immediately know whether the plant is which category. The sun type category of plant or the shade type category of plant. Right. For the CO2 response curve, by playing around, we can also know whether the plant is a C3 plant or C4 plant just by looking at the curve here. I'll put some example here. I'm not saying that oil palm can change into C4 plant, but the C3 plant properties of the oil palm can actually be increased just as good as the C4 plants. Okay, with what? With whatever treatments that you're giving. Maybe a new variety, also a treatment. Maybe you have a pit, right? Maybe you just spray with your pit with a fulvic acid or something. Yeah, or maybe you just want to make the microbes happier. You know, just throw in some Yakult kat situ. Yeah, happy pit, happy bosses, happy me. Right. You change your plant to be so efficient. Now it becomes the C4 plant. Right. Okay. So what? There. Habis dah. Okay. So just that quick overview only for the photosynthesis. Now we want to play around with the machine. Yeah. So you have your machine here. Let's look at the slide, the machine slide. This slide here. Maybe you want to open it already. You can put it here. Tolong dia untuk unpack benda ni, so that you can use your own while I am showing dekat depan ni. Boleh buat depan ni pun tak apa. I'll just Did I do something? Oh, putus pula. Tak apalah, korang tak suka. I'll just put it this way. Apalah, wayang-wayang. Letak je lah atas meja so that you guys can play around. Siapa yang nak main play around banyak tu, have it on the table so that you can see play around. Have you used this before? Main-main ke? No. Sebab apa? Bos tak suruh. Okay. Okay. Yeah, just keluarkan parts saja dulu. We familiarize ourselves with the parts of the machine that you can see. think maybe benda ni kena tembak kesana sikit. Ui, tu. So, so that group sebelah sini boleh guna ni. Group sini belah sini that issue. Kan kena tengah projek ini tu. Tapi wire boleh. Boleh tak tadi? Okay. Okay, now you are seeing that they are assembling the parts of the machine. Remember, okay, this machine can buy a house. Yeah, that you can live happily together with mommy-in-law. Don't have to throw her into the welfare. Yeah. Okay, so let's see what is this all about. What? Oh, person. Okay, so this machine, you need to understand, first thing first, that it has three major bodily components. Okay, the first one is the console. This console, the green box here. This is also regarded as the CPU for the machine. All the computer thing, all the RAM thing. Okay, the console itself comprising of sides or faces. So you got the top face, which is the screen, touch screen, blue light filter and so on. Ada Gorilla Glass tak? This new version of this is actually more robust. Dia lagi tahan lasak compared to the previous version of it. So you have this whatever that you're seeing now, this is the back of it. The front got the LiCOR logo, right? So this is the back of it. So the back of it, we call it the chemical column side. This side here. This is how it looks from the side of it. Okay. So the chemical column side, it has 4 chemical columns here. The CO2 columns, the desiccant column, water column, and CO2 scrubber column, right? And on one side here, the cable side here, this is the cable side. Hasn't got a cable here, but it has been connected here. And then finally, the other side of it is this side. This is the battery side of it. Okay. The battery here is actually rechargeable and it has the power indicator, right? Kind of like a power bank. Right. Okay, go on. Aku lah kan? Suruh orang. Tengoklah. Nyanyuk. Okay, let's talk about I forgot. The other parts for the machine are the cables, the second component of it. 2 kind of cables here. The signals cables and also the gas cables. The gas cable is transparent. So got 2 kind of cables here. And the third component for the machine is the measuring chamber. Okay. Since you have the full spec, the chamber is called fluoro chamber. Yeah. The lower spec, we call it the LED chamber. Right? The even lowest spec, we call it open top chamber. So there are the tiga level. So this is a mirror chamber, or sometimes in literature, this is called IRGA, IRGA, infrared gas analyzer. Right? Okay. So let's look at the, we're coming back to the console, focusing on the chemical sites of the console. 4 chemical sites. So you got the, you got the cartridge? The cartridge. Tak. Tunjukkan cartridge. Kan tadi dah buat keluar chemical. Kenapa di mana ni? Kan sudah buat keluar tadi. You need to use the right cartridge, okay? Maybe some of you have seen this machine before, but the older generation, the cartridge is bigger. This is smaller. Okay? I think it doesn't matter from which company you buy, so you can buy from the third company. The one that you have, that's from the third company, from the food grade. Right? 8 grams of CO2. Or maybe you like to play paintball. They use this as well. Kau tak ada main? You should. Invite, bring along someone you don't like. That's the only time you can do the damage without people questioning your intention. Right? Yes. Right. Okay. So this is meant for this chemical column, the CO2 column. Right. Fair warning, if you use the third party, there is a possibility CO2 can reach beyond 2000 ppm. I don't think people are going to use beyond 2000 ppm. Remember, I said you can change the CO2 to make the plant experience any hypothetical situation. Usually it goes to the maximum of 1600 ppm. Right? Okay. Try not to go beyond that. If you go beyond that, the machine is probably, oh, this thing is busted. Right? How do you think it's busted? If you think it's busted, just change a new one, because it's not that expensive, right? Okay. So the second column is called the desiccant column. This guy here. Desiccant is to remove water. Okay. Maybe you want to study drought response of the leaf, so you can reduce relative humidity in the measuring chamber here. To achieve that, the machine activates the desiccant column. The chemical in the desiccant column is called, the one that I have here is called dry-rite, but I think what you have is not dry-rite. What you have, this thing is Soviet orange. So basically, you can use any kind of desiccants that is easy to find in your locality, right? Silica gel, does it work? It works as well, right? We use dry-rite because we want to look fancy. It has got a color indicator. This thing got color indicator as well. For the this dry-rite, it has the cobalt blue. So when it's pure, new, it looks blue. The moment it has absorbed moisture, it becomes pink. Yeah, and it can regenerate. You can put it in the oven, and then it can be reused again for 3 times. That I'm not sure. Sorbet orange, can it be regenerated? Yes. Can be regenerated as well. So find an oven to dry it so that you can reuse again. But with whatever consumable, usually 3 times is the maximum. After that, not going to do you any good. All right. So the third column is the humidifier column. Previously, LiCOR used material called Stuttgarter mass, but now they have changed it to this tubing. It's called Nefion tubing, Nefion. So you see the little tubing in here. this actually can absorb lots of water. So you just simply put water in here. Siapa nak letak? Pernah letak air ke sebelum ni? Before this? Tak pernah letak air sebelum ni. This in here. Pernah? Kering gitu?
Oh, ada tahu dari kamu dah pergi ke factory.
Pergi ke factory? Is it a new one? No, if it's a new one, you need to put the water the night before. Let it be saturated first. If you want to do measurement this morning and only this morning you add water, you'll be in trouble very soon. Sebab the water will be lost super quick. More suddenly takkan nak buang benda ni kan masih in the middle of the measurement, kan dah ganggu. So the advice is, if this is new, add the water overnight, close it, then you will see the water suddenly disappear. Even if you're not using it, it's just absorb it to all the parts in here. Fill capacity of this thing. Right. What water to use? The best is deionized, demineralized. Okay? Or type 2, type 3 water. If you have a special water machine here. But if you don't have that, you are in the field, go to convenience store, get RO water. You know, RO water in a bottle? Not mineral water. Please don't use mineral water. You might find some problems later on. We don't want any problems because some minerals might get. UHP water is fine. Yeah, because that is type 2 usually. Type 2 or type 1. Yeah. Kowe, okay. Kowe depending on the brand. Some brands, after it has reverse osmosis, it adds back mineral. It remineralizes the water. Some version of the Kowe. I'm not sure which one, tapi ada Kowe yang dia macam rasa, air tu rasa macam air coconut balik. Sebab dia add balik mineral. Itu jangan. Tapi kalau Kowe yang purely RO, then that's fine. Yeah. Okay, RO. Want to add? Silakan add. Add lah. Add. You please don't add all to the brim. Don't do that. Add just below this line here. Lepas tu tutup, tengok nanti. Air kurang tak? Dua kolom.
Kalau spare.
Macam ni. Kalau takut dia tak balance. Oh, dia pandai buat, tak apa. So, korang yang tak betul sebenarnya. Sebab selalu benda sebelah lebih. Ya? Yeah? Duduk.
Dalam bahasa apa kita?
Ya, pusing.
PC itu.
Okay, one thing about this chamber, after you are done with the day of measuring, never leave this column attached to the console. Always release it. Release, cabut sikit. Other column is fine if you leave dekat sini. This column jangan, sebab nanti you will make the condensation in the gas tubing. Yeah. Lepas tu next morning ada Nemo dalam ni. That has happened before. You don't want to turn it into aquarium, this whole thing. Right. Okay. The fourth column is the soda lime. The function of soda lime is to scrub or remove CO2. Okay. The purpose is sometimes it's super difficult to control CO2 in the regular air. Sometimes it is high, sometimes it is low. You just want, for your experiment, the plants to experience constant CO2 concentration. So what the machine does is it removes the CO2 and then it injects back CO2 with the known amount. So that whatever in the chamber consistently receiving 400 ppm CO2, for example, all the time, right? Okay, and then you got your USB port and so on. This part for the data transfer. So if you have, this is another warning. This thing easily catch bugs. If you use impure USB yang tak suci. Yes, very easily. So the warning is, kalau nak guna ni, have a dedicated USB. Don't use USB yang dah pergi 1 cc. Semua dah pergi dah. Don't do that. You don't want all the bugs to get transferred in here. Okay, banyak masalah nanti. Right. Okay, and also you can do the connection cable like what we're doing here today. Yeah, the RJ45 cable, Ethernet cable for data transfer and also untuk screen nanti. Okay, go on. Aku lupa. Tua dah kalau kuku memang patut. I'm aging rapidly these days. Now we look at the consoles. Right. So console here. Tertutup pula. So okay. So the console here, if you open it, this actually creates a separate world for your plant. Whatever plants that you are planting, let's say that I have a plant here. Ibu buat apa ni? Bukan tak happy. Tapi tak ada getah, sumpah aku getah. Guyana chestnut. Oh, what is that? Masak sikit? Sekejap. Okay. So when you have your leaf ready, and then this is the measuring chamber here, you can see there's a light in here, right? There are a few types of light dalam ni. Okay, there is a measuring beam, blue light, red light, far red, saturating flashlight, macam ada lampu dalam ni. Okay, so what it does is it will use different kind of light to trigger different photosynthetic responses, right? Okay. Kenapa dapat pink? Because ada dua, biru dengan merah on at the same time, right? If I want to change into what is it? Cuba change kan? Tutup merah, tinggal biru je. So this is the console. Sini ya, boleh nampak. So now 90% red, 10% blue. So let's tutup warna merah dan keep it. Biru je kan. So this blue is around 420, 440 nanometers, right? Yeah. Buang biru, tinggal merah aja. See? Deeper red. So this is around 640, 650 nanometers. Dia punya right there. Dia ada far red. Dia ada far red. Tak tahu boleh nampak ke tak? Kalau boleh nampak tu, oh. Tak tengok warna far red dia apa? Tutup semua, tinggalkan far red dia. Far red is to study untuk flush electron keluar daripada sistem. Far red is about 740 nanometers. Nampak kan? Ada lah sikit. The usually LED diodes dia bagi energy yang keluar tinggi sikit sebab the moment it reaches your eye, that's actually less energy. Right. Okay. Jadikan setting asal balik. Yeah. So we can play around. So whatever that I just play around, this is light quality or light quantity. Play around with the color. Quality. What about the quantity? Quantity. Turn on balik asal 90%, 10%. Right. So now on balik kan? So now this is the quantity. Keamatan cahaya, the number of photon. Let's make it 200 micromole. Tengok. 200 micromole of light quantity. Sorry? Nampak? Dia redup sikit. Kan? Redup sikit. Try to make it 2000. Dan kat sini. Kan? Dia lagi cerah. Okay? With the cerah, you have more energy. So this is something that you can control with the light. Okay. So whenever you clamp your leaf, make sure that you are touching. Can you see the springy thing in the middle? Itu adalah thermocouple to measure temperature. Pergi dekat measurement tab, page 3. I think number 3 untuk nampak measurement T leaf tu. So now it's measuring this room temperature, which is about 26. Let's say when I touch it. Itu untuk check kesihatan mesin. Ke tak ada jari? Jangan makan. Alamak dah faham. So boleh MC lah. Bye. So it's very sensitive. So what about this leaf? You want to see right? Tengok ni. Let's clamp it. So there is a few temperature sensors in the machine. So we got one thermocouple touching the leaf. Lepas tu dalam ni pun lagi sensor. So kita ada T-air. T-air is the temperature for the gas that's moving in the circuit here. Dalam ni. Yeah. T-exchange is the temperature block ni. This block. Yeah. Yeah. So selalunya 3 itu je we will pay attention to. Right. Okay. So go back to the slide. Let's see. Go back to the slide. Yep. So this is the front of it. You can actually open it. Open bahagian depan ni. To attach extra sensors dekat luar. Sensor lampu boleh, sensor temperature boleh. Maulah. We don't have to open now because you don't have the extra pun. Right. Okay. Go on. Yeah. Okay. Now look at the bag here. Bag ada 2 kan? Ada 2 kan? Kenapa ada 2? To look important. Sorry. So the first bag is the photo bag ni. Ni, semua ni. Jangan masa nak simpan, jangan paksa kalau tak muat. Sebab you are going to break the sponge ni and you might also break the machine. Okay. So masukkan dia di dalam lubang yang betul. Right. The difference between these two bags ada satu je. This bag ada tingkat dalam ni. Lapis. Boleh buka buat keluar masuk lagi. So this is the accessory bags that keeps all the spare part and also the consumable for the machine. Okay. Ni bateri dia. Macam bateri Penang. Boleh ada dia punya indicator. Mana tak indicator dia? Ni. Berapa bar? 3 bar. Right. Okay. Go on. Right. Other accessories adalah macam ini kalau nak bawa pergi field. You want to go to the field, you want to bring. Ada 2. Satu, you can attach the tripod like so here that you guna. Or you want to attach it using the harness here. Okay. You have the harness. I think esok mungkin boleh guna. Pick somebody to become the model tomorrow. Then kau sambung dengan dia. Yeah. Ya, dia tak boleh orang yang plus size sangat. Dia kena yang sedang-sedang. Hebat kan? Okay. Lihat dulu. Okay, now you have learned up to this point. Why not set up your machine macam ni? Buat. Go. Pergilah buat. Come. Mari tolong mereka untuk melihat apa benda dia buat. Chamber dah connect. Isilah chemical column. Oh, the rest nak datang sini nak tengok? Boleh datang tengok sini. Sebab ni dah siap kan? Careful. Air tu kurang tak? Dia kurang tak daripada asal? Kurang sikit. Tak apa. Guna je lah. Saya tengok dekat. So A is the assimilation. Negatif sebab mungkin pokok dia tidur ataupun dia dah. Negatif maksudnya respiration. Positif photosynthesis. Negative means that chloroplast activity less than mitochondrial activity. Now mitochondrial activity dominant. Living cells, plant cells, have two things at the same time. Chloroplast, mitochondria. If photosynthesis activity is small, you got more assimilation, the machine will read positive. Yeah. But early in the morning or at night, mitochondrial activity is more than chloroplast, you will get negative. CO2 reference. Siap? Boleh korang buat. Sebab nak suruh tekan ni, warm up. Kalau sudah tu, now you can press warm up. Warm up, you need to go to set up and then find the warm up test and then press it. Yang ni dah warm up tadi. Press lah. Boleh je warm up sekali ni. Sekejap buang pokok ni sekejap. Press. Tengok siapa siap dulu. Press that. So usually if the machine is okay and healthy, it will take less than 10 minutes to do the warm up. Everything automatic. If something not right, nanti dekat log report ni dia akan bagi tahu. Contohnya macam CO2 tak busted, tukar CO2. Dry right dah exhausted, change to dry right. Yeah. It shouldn't be a problem sebab tadi dah so while dia jalan-jalan, boleh je tekan benda lain.
Yang tadi dah cakap tiga yang penting tu apa tu? Dia extract.
Oh, itu temperature. Muka surat 3, muka surat 1. T air, T leaf, dengan T exchange. Yep. So each page houses different census parameters. Macam page 1, you have the reading of assimilation, stomatophinatum, lampu, semua lah. Page 3 tadi ni untuk temperature. Page 2 untuk you can decide what to fill in here. Edit grade. If you edit the grade ni, you can decide ini nak ada parameter apa. So many. Nanti nombor 4 ni fluorescence ke? Fluorescence. Yep. So F2 is the current fluorescence. So the machine is tengah testing kan. So dia tengah warm up. So nampak bacaan tak betul lah. Bukan tak betul, dia tengah checking all the sensors. Yep. So you can decide, even the graph pun ada banyak, A sampai H. You can change the graph. Macam page A, graph ada double graph, assimilation and stomatoconductance versus time dekat bawah. So it can have dual y-axis. Y-axis is assimilation, y-axis is the stomatoconductance. Itu boleh tukar, tak tukar. Macam ni F is fluorescence. Fluorescent reading with the time. Yeah, if you're not happy with it, macam 0 means now. -4 means 4 minutes ago. Yeah, if you're not happy with that, you want to zoom in, zoom je, cuba zoom. Untuk tengok maybe 1 minute ago saja. You want to zoom, tekan plus. Plus, tekan plus. Bukan betul, tekan handset. Tengok. Ya. Tu boleh unzoom. Tengok. Tekan unzoom. So 0, -4, ya. Jauh dia boleh pergi ke belakang. Macam tu, macam ni. Ya. Asing table macam mana? Nak tutup ni? Boleh je edit graph. Boleh turn off sebelah sini. Dia bagi sini sebab dia nak utilize the screen. Because assimilation and stomatoconductance go hand in hand. If stomatoconductance is low, that means stomata are closing. When stomata close, CO2 cannot get in. Assimilation macam mana nak jalan? Unless kalau pokok tu CO2 sendiri dalam badan dia. Kan? Maybe there is a long lost ants inside crawling about. Insect to respire, keluar banyak CO2. Ya, siap ke?
Macam mana kalau dia dah tu warm up?
Habis.
Oh ni.
Tadi kan tekan start. Ni dia punya progress bar. So when it has reached at the end, that means it's done. The moment warm up is done, then we'll start the environment. Ini tak apa kita buat dalam kelas. Tengok dia orang. Mungkin
Warm up tu memang setiap kali kena
di permulaan hari. So one time only. At the beginning of a day, do warm up once. Sekali sahaja. So meaning that, katakanlah you have done the machine from 8 until 12. Lepas tu nak rest kan, nak lunch, just sleep the machine. Lepas tu when you resume back at 2 PM, no need to do the warm up. Resume sahaja because you have done it during the day. Kalau power off, still okay. Still okay. It's still okay.
the next morning
Yeah.
baru
The reason it has to be once in a day sebab at night pressure berubah, RH berubah. So machine ni has undergone banyak changes during the day, during the night, benda semua. So we need to recalibrate everything. Sometimes it doesn't have to be during the day, a different day you need to warm up. You bring this machine, you have warm up kan, tiba-tiba bawa dia to the peak of Kinabalu. You need to do re-warm up again because different location jauh sangat lah, dah lain. Sebab Kinabalu pressure dia lain. Machine ni ada pressure sensor. Okay, it is in kilopascal, jadi dia ada gyrometer and everything. So you need to tell it, we are 4,101 meter from my home. Itu tak apa, siapa masih dalam kawasan sini. Dia selalu warm up dalam hari yang sama, kena buat banyak kali tu kalau tukar elevation. Ya.
Yang untuk kolom water ni kan, kita perlu buat untuk yang the new equipment ataupun setiap kali sebelum musim.
Tambah air tu.
Tambah air.
Eloknya the night before. Sebab selalunya bila nak mula pagi mesti akan kurang walaupun tak guna.
Maksud kita tambah balik lah.
Tambah balik tak apa. Yep. Just to prep the machine so that while you are doing measurements with the machine, it's not interrupted. We don't want consumable ni tak cukup macam ni tak settle kan. You have one plus to worry about. Lepas tu nak worry about the machine lagi.
Kita masukkan air, lepas tu attach pergi ke konsol ni.
Yep. Kalau kerja kat field, sentiasa bawa CO2 ni lebih. Sebab CO2 third party yang dalam box yang food grade cat lemon tu selalu busted. Macam from 10, mesti ada 2 yang masalah.
Dia akan ada sistem.
Warm up akan fail ataupun CO2 ni sebenarnya tak ada CO2 pun dalam tu. Ataupun dia leaking. Kalau leaking, sejuk. Dia tak sejuk kan sebab tak leaking. Kalau dia leaking dia sejuk. Have a team lah kalau nak buat benda ni. Have a team. Somebody take care of the machine. Somebody maybe tag the plant earlier. Sometimes people they don't plan ahead of time. Sampai kat api baru decide pokok mana. Don't do that. Do ahead of time. Sebab as the time progressing, consumable digunakan. Kan rugi. Mahal consumable kan, nak kena beli. So if you have tag the plant ahead of time, habis satu, go next. Efficient. Right. Ada orang deal dekat nursery. Kalau if you are dealing with plants in the nursery, nak measure photosynthesis, in order to know the lighting, you need to use sensor ni. Nanti I'll show. Ya, ini light sensor ada dua dalam chamber ni. Internal light sensor kat dalam ni. Outside light sensor. Ni silikon. Dalam ni gallium light sensor dia. Sebab dalam ni ada lampu tadi 4 kan. Jadi dia guna sensor lain. Sensor lebih mahal. Mungkin harga Asia. Ini murah aja. Ni harga Xiaomi. Buat measurement. Q in sensor dekat dalam. Q out sensor kat luar. Q out tu. Kosong kan? Cuba buka. Ni. Ada handset. Pasang lampu handset. Situ. Pasang lampu tu dah nyala.
Q-in sensor dekat dalam.
Tak, right. Q out sensor ni. Q in dekat dalam lampu. Ya. Cahaya nur. The good thing is maksudnya from that bright of sun yang photosynthetically active hanya banyak tu tadi je 56. Ya, sebab sensor ni hanya reach between 400 nanometer to 700 nanometer. Whatever before or beyond it doesn't reach. So maksudnya tadi tu lampu handset tu ada sedikit amount of yang pokok boleh guna. Ada sikit dia boleh guna. Sikit lah. Sikit. Sudah ada 10 minit sebab tadi dah macam-macam kan. Dah siap ke sana? Dia dah siap? Setengah? Kita dah habis setengah lah.
Ni lebih sikit.
Lebih kurang.
Jadi kalau sudah pink, kena tukar.
Sikit lagi biru.
Kalau kawasan humidity tinggi, memang akan cepat habis. Ya. Tapi kalau kawasan dekat macam dekat so dia tengah ramping up, so kita boleh tahu sekarang ni dia tengah testing apa. Dia tengah test temperature sekarang. Heat exchange adalah block temperature. Dia change, dia test to the highest to the lowest. Pun dia tak achieve. So meaning that with this equipment, you can create a hypothetical situation. You cannot go to London, but you want to see how my oil palm respond to London condition. Set je lah.
Tapi yang resistant plastic rehat untuk
Itu adalah limit untuk equipment. Ya. Limit untuk equipment. Maksudnya kalau dekat London suhu dia 15 degree, maximum it can go 25 je lah. It cannot go beyond that. Kalau tempat kita, we are about 30 degree kan. We can go as high as 40. Nama equipment yang enables to have that plus minus 10 tu is called Peltier device. PELTIER, healthier device. Dia main dengan current arus elektrik tu, dia reverse. Go forward, go reverse. When it does so, dia boleh change sama ada sejuk atau panas. Ada dalam ni lah, sama dalam ni. Healthier device. Kita nak bagi dia orang siap dulu. Kalau dia orang siap dulu, kita kena cancel. Sebab ini dah siap. Dah. Oh, mungkin boleh pergi ambil pokok dulu kot untuk clamp nanti. Untuk satu grup ni, ambil je lah pokok apa-apa yang mudah. Di sini sudah ada kan? Kalau tak nak guna ni, nak pokok sendiri pun boleh. Atau ada pokok warna tak hijau, nak tengok ada tak photosynthesis? Boleh. Boleh juga. Siram dulu sikit, takut dia tak cukup air. Siram sikit. Siram pokok better air yang mineral lah kalau ada. Siap. CO2 tu tak apa kita boleh ignore sebab dia dah kita guna tadi. CO2 sebab guna third party memang very easy untuk keluar error. Tapi usually you can ignore it sebab kita tahu kita guna yang tak original. CO2 only, okay? Yeah. Alright, so the other group, you okay dah kan? Alright, okay. Once you are happy, let's set environmental condition for your plant. Go to environment tab. Sama dia boleh tekan. Okay. Okay. The other 7 factors that you can set to be experienced by the plant. No need to clamp the plant just yet. Just set first. So the first step is the flow. Tekan flow. Yeah. Flow is the speed of gas movement in the machine circuit. Okay. So you can set it 500. So mari kita setkan sebab kita nak really cepat kan. Kita setkan to 700. Change this to 700 micromole per second. So nanti tekan and then change. Clear 700. And then done. So the machine akan ni lah. Yeah. So and then check dekat tepi ni. Since there is no plant, there shouldn't be any leaking. Alright, ada leaking? Baru kot. Zero. Okay, so all good. So bila dia dah happy, dia akan hijau. Right. Now we can go to the second which is H2O, air. Make sure it is on. Okay. Ada 3 benda air that you can change. RH, saturation deficit and also vapor pressure deficit. But for the sake of exercise, kita set RH sahaja. So RH, ini kena ingat. For tropical plants, the minimum of 50%. Okay. Cannot go lower than that because stomata tak akan buka. Because kita pokok tropika. Okay. So maximum for the machine to handle usually 80%. If we go beyond 80%, nanti ada condensation inside the machine. You don't want that. So for the safe, kita set 60, also, let's say kita set to 65, change it to 65%, done. Okay, yeah. RH at relative humidity for the air. And what? Air yang move dalam ni, yang dalam gas semua ni. Yeah, to be experienced by whatever that you will climb later in the chamber head. Yeah. So it's still yellow, maksudnya dia tengah struggling untuk ni.
Yang ke 20 ke 65?
65 ini. Nampak ni? This is the current reading. This is the current reading. It's increasing tapi dia lambat.
So increasing kalau dekat yellow.
Dia this is the goal, this is the current reading. So dia akan so kita biarkan dia naik. Selalu memang lambat pun. So we can go to next, which is CO2, the thing that you can set. Okay, make sure it is on. CO2, there are two things kena faham, CO2 reference and CO2 sample. Reference means whatever the machine give to the chamber. Sample is whatever balance the plant has used, send back to the machine. Okay, so for our purpose, we set to 400. Maybe kita nak bagi tinggi sikit, maybe 420. So set kan 420. Done. Okay, it is on kan? It is on kan? Tapi for this machine, cuba tengok. The CO2 is not moving. Alright. What does it mean? So there's a good chance it's busted. Ataupun tak ada CO2. Somebody nak tukar? Ambil CO2 baru? Tukarkan? Somebody tolong tunjuk macam mana tukar? Benda ni kena careful ya. If you Sejuk tak? Sejuk tak? Okay. See back the screen. Tengok dia naik tak? Dia naik. Okay kan? So tak apa, biar dia biar. Okay, now you set the fan to 10,000 RPM. Fan is not for cooling. This fan to stir the air inside here. So that boundary layer that you learned earlier is broken. If boundary layer is not broken, CO2 from atmosphere cannot get into the lift. Right. So we usually set at 10,000 RPM. Right. Okay. Then temperature. The air. Right. It's quite cool now. Maybe kita setkan rendah sikit 28. TF. Kalau 30, that's outside. Kat luar. 28. Sometimes temperature is not consistent throughout the day. You just pick an average that you usually deal with that environment. Right. Selalu dekat luar it's around 30 is good. Dekat dalam memang kita set 27, 28. Yeah. So it will start to achieve lah whatever that you have set. Alright. Okay. Light. That's a lot. Let's reduce it to maybe this plant, right? So this plant is experiencing by the window kind of lighting. So that window, what do you think the reading? The reading of my chromol.
What do you think of that?
Actually we can bring machine ni untuk pergi tengok kat situ berapa. Tapi like usually it's around 200 micromole. Okay. Use the sensor outside sensor ni untuk tahu dia punya reading. Then look at the measurement tab. Q out. Q out, which is 3. Yeah. I'm sure kalau kita bawa ke tepi tingkap tu dia akan increase kan. Usually it's around 250. Right. If it reaches 250, you need to increase the light that you set at least 30% more. Yeah, the light 30% more. So 30% extra from 250. Berapa? 325. Ya ke? Petik je. So maybe we want to say that's actually too low. No, the reason you don't want to have lower light because you don't want to underestimate photosynthesis ability, which is incorrect. We want the plant to tell you the actual photosynthetic capability. So shade plant, usually it is safe to set at around 1000. Okay, so maybe light tu tukarkan jadi 1000. Go back to environment. Yeah, the quantity, the set point, change to 1000. Okay, done. Right. So semua dah hijau kan? Semua dah hijau. Now you can clamp your plant. So, sekejap je. Nanti dia hijau lah. Okay, how to pick the leaf? Okay, nak pick the leaf pun you need to know how to. Tapi terpokok betul tak ada, tak apalah. It's about the same. Okay, let's say that you pick one branch. Oh, alamak, dia punya phyllotaxy 4. Yep. Tak apalah. The whole idea is to select leaf that has fully expanded. Bukan mature leaf tau, bukan mature, fully expanded. So it can be a young leaf, but it has fully expanded. Yeah, macam pokok ni is a good example actually. I just want to show you what is meant by fully expanded semua tu. So ini, I just want to see a few. Dia ada satu tadi. Ni. Ya ni. Is this leaf or not? Semua ni shoot. This whole thing is shoot. This is called primordial. You don't call it leaf just yet. But this thing will get bigger, right? It gets bigger. Now it will become like this. Ini boleh panggil leaf dah. Tapi underdeveloped leaf, which is not fully expanded. The cells still experiencing leaf cell enlargement and cell expansion. So jangan tak boleh guna. You need to find bawah, turun bawah sikit. Tengok ni. Is it still expanding or has stopped expanding? Still expanding kan? Turun lagi satu tingkat bawah. Still expanding ke dah sampai ni? Tapi kuning pula, tak cukup zat. So maksudnya 3 level from the top without counting primordial. Macam ni kan? Mungkin primordial tu dah sebelum ni primordial kan? Jangan kira start pada ni. 1, 2, 3. 3 tak boleh guna. Dia selalunya antara 3 ke 5 level from the top. Yeah. So maybe you want to use this. Kalau tak suka, tukarlah dahan lain. Dia ambil ni. Mungkin 3, maybe 5 nampak ikut ke? Bukan jauh dia lebih kecil. This look, okay, number 4. Maybe you want to use this. Claire. What about this? Pilih. Ambil. This bro. Pilih.
Dah 17 dah 17.
Ini semua besar dah. Can I use this? Pilih mana? Pilih. Dah pilih. Clamp. Antara nombor 3 ke nombor 5 level daripada atas.
Tapi di nombor 2 level.
Ini sebenarnya boleh kira primordial lagi ni sebab dia langsung tak habis lagi ni. So dia jangan kira, kita terus sini. This is tingkat 1, tingkat 2, tingkat 3. Tak 3, tak 3 ambil 4. Tak 4 ambil 5. Ini macam dah okey kan? Ambil 4. Besar sikit. Ambil ni. 4. Ini 1, 2, 3, 4. 4. Ambil 4. Ke bawah sikit. Nah. Somebody clamp? Buka clamp tu untuk clamp. Okay, bila clamp make sure touch the thermocouple, okay? Sikit. Touch thermocouple. Oh lupa pula, leaf ni kering tau. Kalau leaf tu basah, lap dengan tisu. Okay.
Leaf tu macam ada debu-debu.
Lap. Jangan dengan wet tisu. Tisu biasa, tisu kering biasa. Okay. So sekarang ni kita dah setkan pokok tu. Untuk permulaan measurement, selalu kita kena meshkan erga dulu. So, eloknya buat tadi masa before you clamp the leaf, tapi tak apa, mesin ni canggih. Dia tahu pokok dah masuk. So, buatlah sama dia buat. Just close this. Press mesh erga. Dah press. Dah boleh. Somebody click this. Okay, tekan auto match. Auto match. Okay, tunggu sampai semua lampu hijau. Lampu hijau nanti dah boleh sudah. Then you can close. Matching is important to tell that the console agreeing with the machine. Ni erga ni. Dia kena agree. Tengok dah okey dah. Hijau tadi dia terus out sebab machine ni sihat. Okay, close. So now pergi dekat page A and then we wait for the stability for the leaf. Now the leaf is photosynthesizing or respiring. So that's dominant. Okay, because stomata. So okay, look at here. So this is the condition for the plant that we choose for this group. After you have clamped your plant, you cannot immediately take the reading. You need to make sure that the plant has stabilized with the current environmental condition that you have set. To know whether the plant is okay or not, look two things, A and GSW. Assimilation rate, which is the Kelvin cycle carbon fixation rate, and GSW stands for stomatal conductors to water. Right. So page A, maybe you want to zoom in this to 0 means now, -8 means 8 minutes ago. Zoom in so that we can say 0 to -1 only. Okay, -2. Zoom sikit lagi. Right. Look at this. And we can use this untuk tengok benda ni. Just tengok ada banyak petak kan? 1, 2, 3, 4, 5. And this is 60 seconds. 60 divided by 5, how many seconds? 12. Lambat. So, one box here worth 12 seconds. Betul lah. Salah, 60 bagi 5 bukan 12. 12, betul lah. So, just tengok kat sini 12 saat. If stomata is going down, the green GSW is the signal of stomatal opening or closing. If it's going down, that means stomata are closing. If you see the green line is going up, the stomata are opening. If the green line somewhat making wavy pattern, stomata are stabling. So that's good. So we want more or less it's stabling. For the assimilation, it's a bit tricky. Look at the axis here. Number one, you need to make sure the axis difference, the top minus bottom, not more than 2 units difference. For example, in here, maximum is 1, minimum is 0.3. 1 minus 0.3, is it more or less than 2? Less than 2, meaning that estimation actually you can accept the reading for now, but is it stabilizing or is it increasing? It's going to increase over the time. But for measurement, the whole idea is to have a quick reading, right, at the real reading. So if more or less the stomata have become wavy and this line is become wavy as well, within this 12-second box, you can log the data. Yeah, meaning that for this time of the day, maybe sekarang pukul 12:30, this is the true estimation reading for the plant. The same plant, the same leaf, if you take at 9 pagi tadi, definitely going to look different. Because this is C3 plant, it's undergoing midday depression and it's going to sleep. It's going to sleep until around 3, then it's going to wake up again. Kenapa? Genetic type, genetic control. Thank you to circadian rhythm. Dengar circadian rhythm, biological clock? Yeah, yeah. However, using this machine, tengok ni, GSW, that's negative actually, meaning that stomata are closing. This is a good sign this plant is following C3 identity, which means closed stomata at afternoon time. We can open stomata. How? Siapa ingat macam mana cara nak open stomata? I said tadi. Buat apa? Siram? Siram nak siram. Light. What about the light? Blue. Maybe you want to increase the blue light? So pergi ke environment. Maybe change the ratio of the blue light. Maybe change this to 15% blue, 85% red. Press. Change. 85 and then blue 15%. Done. Okay. Blue. Change blue to 15. Done. Okay. Then keep it. Right. Right. Sekarang activity we are not looking at assimilation. Okay. We are looking at to open stomata. Okay. Go to measurements. Tengok stomata, can it become positive ke tak? Dia naik sikit kan? Dia naik sikit. You can see the pattern, nampak? Warna hijau. Immediately dia naik. Because we know blue light opens stomata. Yeah.
Adakah kalau kita balik yang blue tu dia akan close?
Dia akan close balik tapi perlahan sikit lah. Perlahan sikit. Tapi it's about if you wait another 2 hours around 2:30, automatically the whole plant akan bangun balik. Itu genetic control dia. Dia macam kan, that time is over. Boss is waiting. Come. Yeah. Okay. Sekarang stomata sudah positif kan, which is good sign. Let's do small exercise. Can we increase assimilation? How can one increase photosynthesis? Kena buat apa? Simply put, but give more photosynthesis ingredients. What are photosynthesis ingredients? Light, CO2, water, everything. Based on this environmental control, what do you think you can give a bit more to the plant so that the assimilation can go higher? Light, maybe you want, yes, go. Check. Go to back to environment. Now you give the light 1000. Maybe you want to increase 1200. Yeah, done. Yeah, so go back to measurement. Tengok. Kena ingatlah tadi berapa? This is light tadi kan? So kita tengok, dia naik ke tak? Tengok stomata, still increasing. This, that it makes a diagonal movement. Maksudnya, this is a good finding tau. Maksudnya, this plant species very responsive to blue light signals given. Because some plants kind of stubborn. Even though you increase the blue light, dia just tak nak buka juga. Maksudnya, plant species ni, dia responsive dengan blue light. Oh, sekarang okay. Okay. So photosynthesis, does it really increase? Very minimally. What else can you give more? CO2. Maybe you want to change CO2. Now at 420, maybe you want to increase about 50 point. So go to environment, tambahkan 50 ppm. Go to CO2. This value plus 50. Berapa jadi? 470. Go. Okay. Then go back to measurements. Yeah. Sabar. This actually, okay. Sekarang ni LiCOR has updated the system tau. There is a new technique to prevent this sudden bumping. Okay, the nama benda tu is in your note actually on the final slide. It's called DAT, Dynamic Assimilation Technique. Okay, so let's activate that. Pergi mana? What does it say on the slide? Go where? Page third last. Pergi setup. Startup. Okay, go to startup. Somebody press on the screen. Go to startup. Lepas tu chamber setup. Go to chamber setup. Lepas tu add dynamic equations. So sekarang ni if you jari tu.
Dari sejuk.
Tak boleh jadi, siku. Okay, dynamic equations ni is actually new invention by LiCOR. Alright, so that instead of waiting, let's say 2 minutes for the plants to stabilize, you cut the time by 60%. It's quicker, right? Right. Go back to measurement. I want to show you apa jadi after you have changed it. Nombor satu benda ni bertukar. You still on page A, but the graph has changed to show you A dynamic is bomb. Don't go there. A dynamic is the original setting that you didn't change before. Purple setting. A STY is the steady state. Terbalik. A steady state is the original setting tadi. A dynamic is the DAT technique. So you can see whether they different or not. GSW masih tetap bersama. Tadi remember, can you apa tu? Unzoom ke sikit 8 minit? Unzoom. Yep. 8, okay. Remember tadi, the moment she changed it to 470, there is a spike. Kalau ni kan. Let's see, kalau kita dah tukar ke DAT, will it have the sudden spike? Or will it not? Kalau ikut nota tu, you are not going to see lots of spiking, which is good, meaning that you can lessen the time that it takes for the stability to achieve. So maybe before DAT time, one leaf you need 2 minutes to measure. Maybe now you only need what? 50 seconds. So it can have a high throughput number for a given day. Alright. Anyway, tadi kita increase the CO2, right? Tengok berapa bacaan estimation sekarang? 3. A lot. What about what? Like, what else can increase assimilation? Heat. Tadi kan ada banyak benda bagi tenaga. You have already increased the light. Tak boleh guna dah. What else can be given to the plant in the form of energy that can potentially increase the photosynthesis? Apa? Apa lagi? Apa tenaga? Selain cahaya, apa lagi? Temperature, kan? Okay, go to page 3. Okay, you set the temperature at berapa tadi? Tn 28. Maybe increase to 30. Tengok, will the photosynthesis get affected or otherwise? Sebab warm kan bagi energy, mungkin biochemical reaction happening faster. It depends on the plant. Sometimes plants tak suka panas sangat. Kita tak tahu pokok dia macam mana. Okay, press balik page ni. Let's see what happens. Nampak nak bunyi kipas tu. So dia tengah acquiring, yeah. So tadi around ni kan, yang naik tu stomata conductance. Kita tengok warna ni, warna zoomkan balik. Zoomkan ni, maybe around my, yeah, minus tu, yeah, fine. Yeah. Okay. Now it is 2 degrees Celsius hotter. But look at the assimilation compared to 1 minute ago. Is there any difference? Macam tak ada kan? Macam tak ada. Maksudnya plants ni boleh tolerate lagi kalau it's hotter. It's hotter. Dia satu je, if you increase the temperature ni, either it becomes more photosynthesis or the plants denature the protein, it go down. Yeah. Yeah. Baik kan? Naik sikit. Sebagai wrap up. Why not increase the temperature a bit more, lagi 2 degree? Let's see what happens. Tambah lagi 2 degree. Tengok tu. Dia dah mula this small exercise to imitate drought condition. Drought condition ada 2 benda. Satu dia panasan, satu lagi kering. Mungkin you want to reduce humidity. Sekarang RH maybe you want to set to 55 or 50. H2O, go to H2O. Yeah, now 65, right? Maybe set it to 55. Less 10%. Yep. Yeah. You don't change the CO2, you don't change the light. Kita sekarang main dengan temperature and also RH. Yeah. Let's see how the plant responds. Sepatutnya dia akan mula turun sebab this you are simulating drought condition. Baguslah, you don't have to wait 50 years until Kota Samarahan become Sahara. Kota Sahara. You can use the machine to simulate future condition. Okay, yeah, dia dah mula turun sikit kan. The pattern, you can see the pattern since 1 minute ago. Dia is slowly turun bawah. Tengok sama mata. What happen when you reduce the ni to 50%? Stomata are closing. Stomata warna hijau hijau nampak dia tutup. Remember, another thing to control stomata in addition to blue light is relative humidity. Okay, the moment relative humidity is decreasing, stomata are going to close, and it's proven here. But turun. Let's increase the temperature another 2%. Tengok idea apa? Oh, that's hot. Dah demam belum? When it gets too hot, it will come to the point, stomata will completely close. You're going to get this negative. Yeah. Sabar. Tengok. There is some people throughout the career just studying about stomata. It's a big subject because stomata is different based on the species. The morphology is different. The physiological response is different. So you got two things to study about stomata on the leaf surface level: stomatal dimension relating to the size, and also stomatal patterning relating to the stomatal density and distribution. Apparently pokok ni buka stomata dia. Interesting. Tak nak pasal dah. Cuba reduce light blue. Tadi blue 15% kan? Revert back to maybe 5% blue, 95% red. 5, okay. And then the red, 95. Done. Turun nak? Interesting. So if somebody were to ask me about the advice about this plant, maksudnya pokok ni it's more responsive to light quality response. You can change around with the temperature apa, dia kind of degil tapi bagi lampu. So maybe this exercise you can repeat dengan your oil palm to see its identity. This is the identity for this one, right? I don't know oil palm. Maybe it's the opposite of this. Yeah. Oh, pun tak ada. Alright. So photosynthesis dah kurang, memang around 3 je. Dia tak capai 4 dah. Okay. So that kind of yeah. Jatuh turun. Macam ramai pula, macam orang tengok bola. Masuk. Yeah, 5% blue light. You see what it does to the stomatal opening. It's closing. Woo, to bawah. Oh, that's interesting. You didn't change the light quantity tau. The light quantity is the same, 1200 micromole. You just change the light quality. Less blue, more red. Sorry. Yep. Okay. Alright. Okay. So in essence, that is how you do the stabilization for the your plant for the survey measurement. If you want to take the data, you want to log this data, you need to create the file first. To create the file, kita boleh create file ni ke? Boleh kan? Create the file. Pergi dekat log setup. Kita dah create file. Open the log file. Maybe you want to create a folder for yourself. Maybe create a new folder. Just your group name. Maybe STROPI something. STROPI. Stress. Stress STROPI. Okay, alright, okay. Okay, done. Okay, select this. Okay, then new file. After you have created a folder, create the file. Okay. So, satu nama file bagilah apa? Maybe nama ni apa? Apa nama dia? Chestnut something. Apa nama dia? Guyana. So letaklah nama apa? Maybe nama chestnut and then date today. Chestnut low blue. whatever dah nak letak lah. Just this depends on the scientist, whatever labeling that you want to put. Sebab nanti bila you transfer the data, that's the name that going to appear on the computer. Okay, done. Done. Let's go to the measurements. Sekarang ni nampak log tab has appeared, meaning that the machine is ready to log any data that you ask it to do. Right. Let's say that you have already with this data. Just kat sini sekali. Tunggu sampai dia bunyi. Bukan itu. Nak bunyi tadi tu. Environment selalunya yang tak stable is water or CO2. It's always good to wait until it's stable, but if it's not stable, you need to use your judgment. Is the stability approaching the set point or otherwise? Yeah. Sometimes dekat field, it's hard untuk reach stability. Tapi kalau dia macam plus minus 5 or 10% from the set point, then that's fine. Because this is something that you can mention dalam material and method. For example, the sentence can become something like this. The set point for the light was set at 1500 mole plus minus 10% of accepting range. So orang reviewer pasti tahulah, oh you set at 1500. Yeah, but plus minus 5% from the set point. Yeah. Okay, so after you have log, if the machine has managed to capture properly, it will become number 1. Alright, okay. So this is the gas exchange mode survey steady state measurement. What about the second one that I mentioned, which is the response curve? Response curve. Mana ni? Hilang. Okay ke group tu? Okay, alright. Okay, let's do the response curve. Kita ada dua response curve boleh buat. Nak buat CO2 response curve or light response curve? Pilih, mana nak buat? Dua-dua? Salah, dua-dua. Belakang. CO2? CO2. Okay. Alright, kalau CO2, I need to create a recipe sekejap. Mana pen? Sekejap ya. Oh, by the way, CO2 response curve lagi susah pada light response curve. You need somebody to advise kalau nak buat CO2 response curve. I'm around tak apalah. I more or less I know apa nak letak. Macam ni, untuk mempercepat keadaan, CO2 reference ni tukar jadi 400. Tukar jadi 400. Apa dah? Oops. Why pardon? Pijak. Okay. CO2 reference change to 400. Lepas tu the blue light change back to 10% blue, 90% red. Cahaya kekalkan at 1200. Temperature bring it down back to 28. Untuk buat CO2 response curve, other parameters kena stable, tak boleh extreme. Because you are going to have extreme CO2 very soon. So Sekejap ya. Okay. So, lepas tu pergi ke sekejap, I need to recall balik. Cuba pergi dekat constant. Tekan constant. Sekejap ya. I need to tengok parameter tak ada, environment setup. Tak ingat kat mana. I need to bagi tahu kat machine sekejap. To set up. What about here? Tools. Environment tak ada. Program log setup. Okay, kat sini. Tekan stability. Ni tak ada. Matching option. Okay, sebab kita nak buat CO2 reference sekejap ya. Only CO2 mesh if delta CO2 okay, betul. Reference change those 10 minutes. Uncheck this. Oops. Uncheck this. CO2 air tak payah match. Okay, betul. Okay, biar je macam ni. Okay, go back to measurements. Go to measurement. Okay. So, we allow the plant to acclimate sekejap dengan this condition, but at the same time, tapi tu stomata tak buka. Kejap ya. Degil stomata ni. Basah tak? Siram sikit. Siram pokok ni. One thing to remember, if you want to do CO2 response curve, stomata memang kena buka habis-habisan. Otherwise CO2 tu macam mana nak masuk? At least dia positif. Tukar balik blue jadi 15% blue. Kita kena buka stomata ni. Ya, betul. 15%. Okay.
Dia punya apa tu? Reading untuk semata portfolio.
That's the thing. It depends on the plant. Lagipun sekarang ni dah pukul midday depression. Ya. Tapi we set minimum RH. Oh, RH tadi dah increase 60%.
Belum,
65.
masih 50.
Sebab tu dia tutup tu. RH lagi.
Tak apa lagi.
60 kan? RH 60.
RH 60. One.
Kenapa dia lagging?
Ada hikes.
15, okay. Done.
No. Dia tergerak.
Apa? Biar dia sekejap. 151. Itu dah 105. Kenapa dia lagi? Rasa tu sih. Okay, keep. Okay, RH tu naikkan 65. 65. Patut semata tutup, dia dry. Okay, alright. Go to measurements. Sekejap, tengok stomata tu dah positif belum? Belum. So tak apa. In the meantime, while waiting for this GSW to become positive back, go to programs. We need to tell the machine to change mode to response curve. Tekan ni. Find CO2 response. Okay. Sekejap. Sebentar. Bagi dia keluar setting. Okay. CO2 target, ni tukar jadi CO2R. Adakah CO2R?
Saya seseorang perlu tolong rem macam ni.
Dia lagging sikit.
Sebelum ni belum tambah lagi kan.
Kenapa dia? Aku sebab connection tu. Tapi sekarang tak ada apa kan?
Saya keluarkan ayam kat atas tu. Satu jari ni.
Atas mana? Ada. Saya tak nak klik.
Oh, 5 masih ke?
Okay. Alright. Yang ini CO2 values ni ikut ni. Start from here, continue here, continue here. So this is the final point. Sepatutnya ada 11 points. Start from 400, 400, 300, 200, 10, 50.
Banyak pun belakang kan? 900, 1000. Oh, betul.
Okay, kira betul tak ada 11 poin? Ngam. Okay, done. Sebentar. Okay. Sekejap. Jangan, nanti kejap. Okay, go back to new measurement. Okay, dah positif? Dah positif kan? Dah positif. Tapi tengok, kejap. Tengok ni. Stomata ni still tak settle lagi. Dia tengah buka lagi. Dia still nampak meroket ke atas. Dia kena wavy macam tu baru dia stable. Sabar. Dia kalau dia dah wavy sikit dah boleh dah relax. Jangan dia nak turun pula dah. Stomata tutup. Okay, so one point about stomata phenomenon in stomata. Kalau sometimes nampak macam ni, this condition is called patchy stomata. Patchy stomata meaning that for a given leaf area, macam ni, there are millions of stomata. Not all of stomata open and close at the same time. Some are open, some are closed. Even stomata yang clamp in the circle dalam ni. So bila ada yang kejap buka, kejap tutup unevenly, so you will get the hump. Macam tu. Alright, okay. So I think this looks okay now. Boleh mulakan autoprog. Go back to program. Lepas tu boleh start. Kejap. Tak, group belakang tu. Make sure macam ni juga. 30 to 120 seconds. This group tak apa, itu memang betul lah. Group sana.
Biasanya
Okay, boleh kan? Ni nak pergi apa? Nak pergi minum, pergi apa sempat bayang ni?
Okay, nak makan dulu. Kita pergi lunch. Kita pergi lunch.
Boleh nak pergi lunch? Boleh.
Semua kat sana.
Nak pergi silakan, boleh. Nanti dah sudah nanti dia tutup saya.
Baiklah. Kita pergi lunch dulu. Lunch kat Commandery.
Okay.
Lunch.
Nak meeting apa Haji tak kejap? Push mana? Kata nak meeting pukul 1. Kau nak makan, pergi nak makan dulu.
Lepas lunch kita atur.
Okay. Boleh. Jom. Tolong charging ni balik. Pause kejap. Ini tak apa kan, boleh biar je kan? Stop. Is it done? Okay, so it's done. Now we need to close the file so that it's not lost. Close. So to close the file, mana rotan? Rotan. Apa nanti we take dulu data and nanti kita guna untuk interpret. So to close the file, pergi balik dekat go to log tab. Is this thing on? Okay, close log. Yep. Done. Okay. Nak confirm the file just now captured or not, you click dekat your own folder, see, then click this button, the roll down button. Ya, ada file dia kan? So ada. So the file will come in the form of Excel file. Okay? So nanti we will have a look how to extract out the data. There is a slight change with the flow of the lesson. Okay. I'm thinking we can learn separuh about fluorescence hari ni and then kita sambung lagi separuh esok. Alright? However, data fluorescence boleh ambil hari ni. Cuma kena adapt sekejap. So tadi students dia dah adapt the plant. The best is to adapt overnight. But since tempat ni it's not that bright, the minimum of 30 minutes is enough. So this has been about 10 minutes. So we leave some for a bit. So what we can do now is the plants that are present in here, if you want, we can have another set of data like response curve. So while the response curve is running, like CO2 response during lunchtime tadi, kita boleh belajar fluorescence. Just let the machine run. Okay. So for light response curve, create new log files under the same folder. Tadi yang ni kan, yang ni sebenarnya ada data CO2 response curve. Tak apa, boleh edit kemudian. So just create a new file. Tapi this time memang dedicated untuk light curve, chestnut light curve. Yeah, ataupun for the short of it. LRC. Yep. Okay. So done. Okay. Right. Cuma go to the environment. Set light to be 1500. Light to 1500. Done. Ya. Nampak tak CO2 ni? Kan tinggi? Because that's the final point tadi kan? Set ni balik ke 400. Okay, 400. So go to measurements, tengok the stability of it. I'm going to write dia punya sequence untuk light. Okay, RH masih sama. Okay, tengok measurement ni. Tengok dia punya stable tak. So, simulation sekejap di tengah bangun. Tunggu sekejap di tengah ni. Tadi, the last point that you stopped was 1200 CO2, right? At high CO2 concentration, stomata almost tutup. Itu memang rule dia. High CO2, close stomata. Low CO2, open stomata. Right? So we need to open the stomata sekejap sebab kita kena make sure benda ni ada jadi positif. Masak tak ni? Just make sure dia... Boleh siram sikit lagi? Siram sikit lagi. Okay. Itu pun boleh siram juga sikit lagi. Sikit lagi sebab nampak estimation tengah naik. This is the sign the Kelvin cycle is recovering. Nampak estimation tengah naik. Stomata pun tengah buka. So tadi negatif kan? Approaching positive. So tadi kita tahu based on this setting at least boleh dapat around 3-4 something the assimilation rate. So that's what we are trying to do. So while waiting for this, go to program and find light response. Yeah. Tukar ke Q in tu jadi reference ni. It should be 11 points including the 0. Cuba kira, cuba 11. Okay. So done, tapi jangan run lagi. Okay. Go to environment, make sure dark path tutup. Pergi ke environment. Lepas tu light. And then in here farad. Okay, farad ni tutup. Okay, tak apa. Dia dah zero dah. Dia dah kosong. Yeah. So boleh keep. Yep. So go back to measurements. So let's leave sekejap ni bagi dia naik sikit. Okay. So the way it works, tadi CO2 response curve, the direction of the CO2 go down and then up. Balik. Itu CO2 response. For light response, dia tak macam tu. From the highest all the way reverse to the lowest. Dia lain. There is a biochemical reasoning behind it. Right? Okay. So while waiting for this to happen, what about the other group? Is it okay? Okay kan? Belum lagi. We leave it at least. Yang ni tadi we know it's capable to be around 4 something kan? 3 something or 4 something. So kita biar dia sekejap. Okay. In the meantime, while dia tengah biar tu, let's learn about what is fluorescence for a bit. So boleh buka nota yang the final page of this mana tak? Ni. Screen ni boleh tukar jadi ni tak? Yang ni biar je sebab kita tengah acclimate dia. Tukar screen ni jadi ni. Maksudnya yang nombor 2 lah kan. So dia pergi sini, 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 sini. Okay, alright. Take a deep breath. Okay, buang jauh-jauh negatif aura. Kan, make a doa, nak baca doa, this is the time. Bacalah doa. No, I'm a bit worried sebab I've been teaching fluorescence dekat Malaysia for various groups. Hardly people can catch it. Kalau dia catch it pun kejap lepas tu dia lupa. For some reason, tak tahu kenapa. Mungkin sebab this is physics kan, maybe kita tak ada, masing-masing tak ada background physics. Tapi let's put it this way, just be open mind about it, and then cara cuba faham dia adalah you need to create analogy which looks and sounds familiar to yourself, right? I tell you what, fluorescence kalau mahir, you can go very far. Sebab it is not only for plant science, it is used in banyak lagi industri lain. Material science, NASA, astrology, semua tu fluorescence tu. You can go far. Maybe you are tired working as STROPI after 10 years. I want to go to NASA now. Go. Okay. Right. So look at this image here. Yeah. This is the cross section of a regular leaf, and we know that there is a layer of transparent epidermis, and then inside of it, there's a bunch of mesophyll cell tissue. Palisade mesophyll, spongy mesophyll. Light coming and then hits all of these cells. It has destiny now. Light hitting this plant. What will happen to the light? Okay, so these are the destiny of the light that gets into the transparent leaf. Okay, number one, it can be maybe get reflected, which actually most of it dipantulkan, or diserap, or actually get transmitted. Okay, so we don't worry about this reflection. We don't worry about the transmitted. We worry about the one that actually get absorbed. Okay, light that get absorbed into the leaf has further destiny. 3 destiny. What will happen to the absorbed light? 3 things. Okay, either it will do photosynthesis, then you get all your photosystem and ADPH, ATP, and so on. Or it can be released back in the form of heat, or it will fluoresce. Okay, 3 destiny of light that has been absorbed. Right. So what exactly is fluorescence? Go on. Ooh, what's that? Okay. A quick repeat from the light or photo reactions that you learned this morning. Light that hits the island of pigments in the leaf will be passed around, not because the pigments like to play ping pong. It's to reduce the energy so that it hits the right energy to activate reaction center. The moment reaction center, which is a special chlorophyll A molecule, gets excited, an electron will be ejected out. This electron is the one that run electron transport change and causing all the reaction to produce an ADPH and also ATP. Right. However, sometimes the light, oh, by the way, all the pigments that are not involved in photochemistry, but rather as antenna together as much, we call it antenna complex. There are many antenna complex in the leaf. Red, maybe red and purple, it can be anthocyanin. Orange and yellow, that can be carotene. You know carotene, like the carrot? What else? Warna apa lagi? Kuning, xanthophyll. That's yellow in color. Okay, blue, maybe phycocyanin. Okay, there are so many colors that can be present depending on the species. Even if I only talk about chlorophyll, chlorophyll also has variants. Chlorophyll A, B, C, D, and so on. Right? Most of the chlorophyll that present in the island of antenna complex, those are chlorophyll B. Right? So the absorption spectra of chlorophyll B is different from chlorophyll A, slightly different. Okay, right. So the light coming this way, if it proceed with this is one of the destiny of the absorbed light. We call this light has taken the destiny of photochemistry, which is what you want. Because this is the destiny of the light that will help you to get sugar precursor eventually. However, you just learned there are two more destiny. Go on. Let's see. Okay. Oh, before I go to the two more destiny, what this is what happens at the special chlorophyll A molecule, the P680. The electron gets excited. That is synonym when I say the electron gets ejected. Okay, then it will go down. Going down the hill, the capturer is the electron acceptors such as quinones, plastocyanin, and also cytochrome B6F that you saw earlier today. Go on. Yep. It's different this thing. Yeah. Okay. I think I used the wrong, no, not wrong, incomplete image actually. There should be like two destiny of light. Actually, there should be a two destiny of light here. Maybe there's, you should jump to slide number, sorry. Yeah, maybe slide after this. Jap. Apa mana benda ni? Oh, one before that? Oh, yeah. Yep. This slide here. So, the other two destiny of the absorbed light. The one here, photochemistry, that's fine. This proceed with the electron transport chain. This thing. It can be either released back in the form of heat. Remember, you know today, heat is light. Okay, heat is light. Meaning that your fever friend is bright. So bright. The hotter she is, the brighter she looks under the camera. Right? Ching. Okay. So what exactly is fluorescence? Fluorescence is actually the phenomenon of glow in the dark. Remember in the past when you were, pocket, you have an analog watch. The clock hands. When you go to the dark, it looks what color? Green. Okay, that phenomenon is called phosphorescence. They use phosphorus for it. Phosphorescence. Many chemicals can be used. That one is phosphorescence, right? Because when the analog clock or watch has been exposed under the light for quite some time, it absorbs all this energy and then keep it in the molecule, the green molecule. It keep on releasing. However, during the daytime like this, you don't see it releasing back the absorbed energy. The moment you go into the darkness, you start seeing the release of the absorbed energy. This is what you see actually in the clock. So when we talk about plant fluorescence, that is the glow of the dark by the leaf. However, not in the range of light which can be detected by human retina. Okay, remember one of the slides, there is a cross section of the eye, the retina at the back of your eyes, and then there's a photoreceptor cells, the cone cells and also the rod cells. Those cells have limitation to only detect light from the wavelength of 400 to 700 nanometers, right? So whenever fluorescence, which usually happening 740 nanometers and maybe longer, your eyes cannot see it. Okay, and the plants keep on releasing this. Okay, this machine is equipped with a special sensor just to detect this fluorescence. Okay, at specific wavelength. I think it's around 740 nanometers. Okay, this is the definition of the fluorescence that most plant scientists use to detect the event of fluorescence. What about the heat? Anything that get released in the infrared region. Okay, usually it is negligible because leaf inside of the leaf tissue is wet. This is all, inside the leaf, all water. So the moment there is a small heat release, no machine will be able to detect the heat. It will be immediately absorbed by the water, the tissue, the water in the tissue. Your machine is outside the leaf. How is it going to measure the heat inside? So that's why most equation consider heat release as negligible, right? However, the fluorescence at specific wavelength, 740 nanometers, for example, can be detected very easily, right? If you think about it, do you want the leaf to fluoresce less or more? Which one do you think is the best situation in terms of photosynthesis? To release more or less fluorescence? Less. Why? Exactly true. Because if it releases less fluorescence, more portion of it has gone through photochemistry, right? So this is what we're trying to learn with fluorescence, right? Go on. Yeah, something like this. Yeah. This chlorophyll molecule, it gets excited. This excitation has this destiny now. Can it be more than 4? What do you think? Can it be more than 3 destiny for the light? Maybe can. If somebody got boring, scientists got boring and has nothing to do, they decide to divide heat into 3 sessions. Heat 1, heat 2, heat 3. You know, some scientists, they like to make us suffer, right? Got boring, stay under not coconut, apple, make calculus book. Then you got to learn calculus. Right. It's a good thing it was an apple. Imagine Newton stayed in tropical and then he decided to stay under coconut tree. If Newton used coconut tree, you wouldn't need to know calculus. Jatuh, pak. Tak sempat nak fikir. Why gravity? Okay, alright. So let's focus on this now. So we neglect this, and this one will come a bit later. Okay. So we focus on these two now. The one that gets absorbed, and then the one that will fluoresce. Okay. Go on. Let's zoom in to look at what exactly happened in an island of antenna complex. Remember, one island of antenna complex will have one reaction center, that is the special chlorophyll A molecule, just like this. So when you see in journal or book, when it says reaction center open, it means that the chlorophyll A molecule has ejected out its electron. It has become excited because it has absorbed the right amount of energy. Then it kicks out the electron. Now there is literally a hole in the molecule. And this situation is called open reaction center. Right? Okay. Yeah. So again, I like to put this many times so that people understand the transfer of energy. Because people keep on forgetting, light that gets transferred around will be higher in nanometer, but will be less in energy. It's opposite. People keep on forgetting that. So passing around. You see, this is completely open, right? The energy will jump into that. However, go next. Okay. What happens if the reaction center is closed? Meaning that the chlorophyll A molecule still has its electron intact. That electron cannot be absorbed into the photochemistry, and it will be released in the form of fluorescence. This is why with the reaction open center, the fluorescence event almost zero. This is for a perfect system. Remember, okay, for a LiCOR membrane, remember the green pancake that you saw earlier today? On a single pancake surface, there are millions or maybe billions of these islands. This is only one. So many of that, right? So when some islands are open, the fluorescence will be almost zero. Okay, 100% light is utilized for photochemistry. However, if the reaction center are closed, the light has to go somewhere. Photochemistry is not possible, then it will choose either to become fluorescence, glow in the dark that the machine can detect, or it will just dissipate as heat. Okay, the plant try not to dissipate in the heat for good reason, because heat can compromise the integrity of membrane in the cell. So it's better to release as light, right, rather than heat, right? Yeah. So F naught or F0, no fluorescence. F max or maximum fluorescence is the maximum amount released back by the absorbed leaf. Okay, so to put this into perspective, when you look at your leaf like here, just to test your understanding. So you have two leaves here. The leaf that has been covered for some time, and the leaf that is in here, which is continuously under the exposure of light. Tell me now, this operation center, the back leaf or the photosynthesizing leaf? This one. Operation center. The back leaf or the chamber leaf? Aku cakap masa kau tak faham. Who says chamber? This operation center. Who says chamber? No, I just need to see whether. Who says chamber? 1, 2, 3, 4, 5. 6. Banyak lah. Okay, most cakap chamber. Why do you say this is the chamber? Think this way. The leaf in here is being constantly bombarded by high energy. Okay, meaning that any pigments in here are being busy absorbing energy. super busy. When it is super busy, would it be more holes or less holes? Almost no holes actually, because any possible holes, photons plug in. So actually, the one in here in the chamber is this. This. The one that has been back will be this. Because what? Because whatever photonic energy left behind has been cleared by the photochemistry until there is no more energy left. So the whole reaction center stay whole, berlubang lah sampai the next energy coming in. It's okay, ramai je. It's not just you. Ramai orang sangkut benda ni. The concept of open and closed reaction center. Yeah. Can you understand it? Think of it this way. This guy here, I just gave this analogy to Indian people and they seem to get it. Maybe I should repeat the analogy again. This guy that has been back is makeup okay, get motivated, optimistic, and not knowing what's behind the door waiting. Right, very ready to undergo the day. So at 8:30, suddenly you got your first job. You happily accept the job and deal with it. Right, because you are completely open to any possibility for the day. That's you at 8 a.m. Yeah. This leaf here has been utilized for quite some time, is equivalent to you at 4 p.m. What happens after the whole day at work? Makeup is gone. Right. Don't touch me, I'll kill you. Right. The boss, when are you going? You already have a lot in your hand. Suddenly, that inconsiderable boss behind the door throw you another 3 assignments. Now, ambil. What will happen to you? Can you take more job, or are you going to throw it out of the window? You at 4 p.m. is this leaf. You cannot accept anymore because there is no more hand to capture. Just throw it out of the window. That throwing out of the window is this maximum fluorescence. Get it? Oh, jauh aku cerita. Itulah equivalent dia. Has been utilizing, has been busy, has been working non-stop. If you give any more, it's true. This is going to be open and closed, like so many times for 1 second. But when you are working for non-stop, the rate of you finishing the previous job gets slower and slower and slower. Your productivity has declined substantially. Yeah, that's 4 p.m. Let's try 6 p.m. You got overtime, right? Yeah. Suddenly, boss called, come meeting. This is for the group, one for the team. Yeah. Can you put up the happy face? Yeah. As the time progressing, you can handle less and less to make this open again. Unless you go back home and let's put you on the bed, cover you with blanket like this, dark adapt you for the whole day, then tomorrow we open again. Then you can become like this. Then you're ready for the next day. So macam tu lah juga plants. Right, okay. Go on. Ooh, what's this? Yeah, this is actually the concept of reaction center. This slide is actually from the previous talk. Don't worry about this. Don't worry about this. Don't worry about this. Look at this only. Because this actually talks about the chamber here, the chamber here. Remember, I told you that there are many types of lights in this chamber? Okay. When light is completely off, no light is turned on, visible light off, invisible light off, everything off, that is this thing, the baseline. Complete darkness. Okay. However, when you turn the first light, which is called measuring beam, you will start to have F naught. Okay? Meaning that this light, when it is shown upon the leaf surface, it is enough just to trigger fluorescence, but not enough to undergo photochemistry. Yeah. It's completely like the leaf receives the light. Since the light is not the right wavelength, it is not absorbed or put into the hole. It's completely released back as fluorescence. 100%, 100%, 100%, 100%. Pretty much like you being called to 8 p.m. meeting pula sekarang. The boss keep on giving you tasks. Actually, you cannot absorb anymore, but you are putting up the smiling face. Completely cannot hear anything. Blank. People can throw you all the stories, all the job tasks given. It seems like you are accepting it, but you know, it's completely reflected back. Right? Okay. And there is another kind of light, we call it saturating pulses. When this is activated, this is when you will get FM, maximum fluorescence. Okay. Oh, by the way, sometimes in the machine, I'm not sure about this machine, sometimes in literature, F naught is labeled as FS. S stands for steady. Steady fluorescence, right? So look at this, FM, maximum fluorescence. So what is the saturating flash look like? So this machine, we can set the saturating flash up to 16,000 micromole. Yeah. Just now you give 1500 micromole, right? You can set the saturating flash to be 16,000. Flash on the leaf so that you can get maximum fluorescence, right? Immediately after this has been done, the fluorescence signal will drop back to the F naught place. The difference between maximum FM and the baseline FO, this is called FV. That V stands for variable fluorescence. Yeah. When you bring these two together, you already have the first parameter in fluorescence photochemistry. Right? Go on. Let's see. What's next is after that? Yeah. Oh yeah. Quick recap. So this is what I have explained just now. Right? And the next type of light is the light that you change the set point 1500, 1000, the blue 10%, 10%. Those kind of light is called actinic light. This actinic light, the light that will actually cause photosynthesis to happen. Not just to emit everything back as fluorescent. We want this light to actually go down the photochemistry line. Right. Yeah. So this is the whole exercise to do fluorescence. However, I'm not going to go until the end because this will involve very long story. And since you are not dealing with herbicide, for those doing herbicide study, I will teach until the end here because we need to understand the mode of mechanism for herbicide. Right. So darkness when the actinic light is on. Okay. So can you see the apostrophe up there? That is the prime signal. The way you say it, FM prime. Prime means light adapted leaf. Leaf that has been subjected to lighting for quite some time until it has adapted to that level. So in physiology, we denote that as Fm prime. If the M doesn't have any prime marking, automatically assume as dark adapted. So that this is the conventional notation for fluorescence. Even if you are dealing with other fields, not just only plant physiology, you go with material science and so on, this is the same notation, right? Okay. So what about all of this? Okay, not to worry about this. I think that's enough up to that point. Good. Go further. Yeah. Okay. So knowing all of this FV, FM prime, and so on, will create these parameters. Okay. Okay. Don't change phase. I'm not going to shoot you with all of this. Today, for this session until tomorrow, we only deal with two things. We deal with FVFM and also phi PS2. Two things only, right? Okay. FVFM, that's easy. You have seen how you got it. What about the phi PS2? The formula for phi PS2 is you need to get the Fm prime, minus it with F prime, then divide it with Fm prime again. So how do you know which point of the lighting? Go back one slide. Where is Fm prime? Over here, right? Meaning that you turn on the light and you let it acclimate to a new light until it has stabilized. Give the saturating again, meaning that this leaf has been in here for quite some time, right? This leaf actually in this region here. If I decide to press the saturating pulse, it will flashing in here. That flash will result in Fm prime. Okay? So you got it now. Go one slide. You got it. Then you can get phi PS2. Phi PS2 is the photochemistry efficiency. Right. Okay. Go further. Yeah. Yeah. So this is the detail of it. Okay. In case you missed something. Wait. One slide. Oh, no. Next. Next. Yeah. No lighting. Measuring beam on. Then you start to give this, and then when it goes down, you got FV, FM. This is the you can tell whether your plant is stressed or not by using this parameter. Maybe some of you are studying plant stress, right? FVFM is a very good measure because the reading of FVFM is highly conserved around 0.8. So what does it mean 0.8, 0.85 like this? The machine, it knows how many light particles it gives to the leaf. Okay? And then the sensor will measure back whatever the leaf throw out of the window, not using. I'll give you an example. LiCOR give 10,000 light photons to the leaf. Right? From these 10,000, we know that not all are going to be absorbed by the leaf, right? Some are going to be reflected back or released back. If the sensor detects, it gives 10,000, but it detects back 8,000, then it knows. Oh, sorry, not 8,000, 2,000. It gives 10,000, but the sensor detects there is a unused photon of 2,000, meaning that the reading of every FM here is called 0.8. 80% of the given light has been absorbed into the leaf. 20% is happening other direction. Okay. However, this is not a complete story. 8,000 photons that is absorbed, that is just absorption. The leaf has not utilized this photon yet. 5 PS2 will tell you out of this 80% absorbed light, how much actually undergo photochemistry and give you the photosynthesis product, NADPH and ATP. Alright? Okay. And FVFM, this is the name, maximum quantum efficiency of photosystem 2. If you measure FVFM, different leaves in here, if they are healthy, regardless of the age, they are going to be the same, around 0.8, 0.81. Yeah. But suddenly, if one leaf, maybe the one down here, if you measure the FVFM, it's going to read maybe somewhat 0.77. To our eyes, 3% is not that different, right? But to plants, this is a signal. This leaf is either stressed or it has gone senescence. Yeah, because it is highly conserved. It's not easy to change FVFM even if you put lots of fertilizer. So it's a strong indicator of the plant stress. Okay, stress not only water stress. It can be salinity stress. How can you stress plant? Put it in front of your friend, looking at your friend. Stress. How can you stress your plant? Hit, kan? Hit, cut, yes. Ni, goyang. Violently, kan? Kiri kanan, kan? Maybe cursing. Yeah. Here's some of you are very creative with words using. Use all those words here. I don't know. You know, each state. I don't know about this state. Each state has their own set of words of choosing to use in the times of emergency. Just to highlight the point. So maybe you can use this use of words on this plant. See what happens. Some people do the study actually use the good words and the cursing words. That actually do something to the plants for some reason. Yeah. Right. Okay. So go on. Yeah. So I show here some publication data. Just by having FVFM, you can have something like this. By differing the time of the day, you can see that the plants actually have less FVFM, but since it is a healthy plant, perhaps the FVFM is going to revert back to the normal value. Right? It's not easy to change it. Even though it looks down, maybe in the afternoon time, it's super stressed with the hot condition and everything. But if it's a healthy plant, it will come back to the original value. Yeah. Yeah. Right. But if the plant is not so healthy, maybe it will go down and never coming back. Yeah. So you can use FVFM just as a quick measure to understand whether your treatment has incurred serious effect or not to your plant. Phenotyping. Ever heard that word before? Plant phenotyping? FVFM can be used for plant phenotyping. Yeah. Yeah. Just kena dark adapt. What if you don't have time to dark adapt 100 plants? Do it 6 a.m., 5 a.m. Yeah. Don't have to bag it. Let's say, do you have the 1,000 plants? You want to bag one by one. So do it maybe 4 hours after the sun has set. Sunset at what time here? 6. Around 6. Right. Around 6. So start 10 p.m. You can start doing the FVFM. No need to bag it. Yeah. Or because 10 p.m. that's the prime time for the family. Oh, it's okay. I'll just wake up early tomorrow. Then do it at 4. Right. That is acceptable as well. Right. Just remember, if you do it 4 p.m. because I've done it before, the plant is going to be super wet. You need to properly wipe it and so on so that you don't hurt the machine. Right? Okay, go on. Yeah, another samples of this technique. However, this thing adds a QP and QN. We're not covering this today. This is the photochemical quenching efficiency for the plant. Yeah. Yeah. Okay, go on. Go on, let's see. Yeah. What about the 5PS2? By the way, I just want to say, look at this. Okay, this group, I think your estimation has stabilized. You can write your light curve now. Somebody come to press the program and start the light response curve for that group as well. Programs. Yeah, just start it. Yeah. Sebab file tadi dah ni kan? Dah mula. Has it started? Yeah, started. Alright. Light response curve is a bit quicker than CO2 response curve. So maybe we can get this reading in about 10-12 minutes. Yeah. Yeah. So this has been started, okay? Sekejap je. Oh, lupa nak tukar ni, tak apalah. Selalunya I just put it to apa, sekejap je. Itu sampai 3 minit. Tak apalah. Tak apa, this early mesh is allowed. So that should be a problem. Yeah. Okay, coming back to here. Yeah. Right. So for the 5PS2, what is it actually? So you got the FVFM of the reading 0.8, meaning that 80% of the light is absorbed by the leaf. Now you want to know from this 80% of the leaf, how many actually doing the photochemistry work? Or you just, lounging around, just stay there and look pretty. Plants need to use it as efficiently as possible, right? So this is what light adapted is needed, okay? So after you're done with FVFM, turn back on the light and let the plants to undergo a steady condition like what you're using now. Usually it takes about the minimum of 15 minutes. Minimum, I say 15, minimum, it can be longer. So that's why if you are doing this study, FVFM and 5PS2, it's a good idea to do it on separate day. Because you can keep the FVFM in one file and then tomorrow resume back the file for the 5PS2 experiment, right? Okay, so go on. Go on. No, this is FVFM. Go on. Yeah. Effective quantum yield. 5PS2. Phi is the one of the Greek letters, okay? Not pi. Pi 3.142. Itu pi. P-H-I. Phi. Phi. Phi usually people in scientists use as a symbol for efficiency. Right. So that's the formula and then you got it. Right? Measurement of this parameter at certain irradiance value. Ability of organism to move electrons beyond photosystem 2. To where? To electron transport change. The moment electron transport change is moving with busy electrons, then that's when you got an ADPH and ATP to run your photosynthesis. Right? Remember, without the product of photoreactions, Kelvin cycle is not going to cycle. Kelvin cycle, the word cycle, because it needs energy. Energy come from where? From the photoreaction. Right. If the photoreaction is not producing energy, Kelvin cycle, say bye-bye. Right. Go on. Yeah. This is a good example from a paper. Only use these two parameters to show the effects of I think they were dealing with micronutrients, copper and zinc. So you can see that day after treatment here, this is the FVFM, the top, and then this is 5CO2. PS2, sorry, 5 PS2. There is another 5 CO2, but we're not going to go there. Let's look at here. Control 50 milligram, 100 milligram. What will happen when you don't give enough copper or you give extra amount of copper and zinc? What will happen? And then this is days after treatment. At the beginning, at the base level, the control kind of have similar FDFM, right? So what will happen with the 5 PS2 at the beginning? You can see that 5 PS2 do not have the similar trend with FVFM. Clearly, this control thing has higher 5 PS2 compared to the other. Right. So that's why I always say if you do FVFM, that is only 20% of the story. Because we do not know the absorbed photons by the leaf, what happens to it. Unless if you do the 5 PS2 quantification, then only you know what will happen to it. Yep. So eventually, if you add lots of copper, will it help with the photosystem efficiency? No. No. At least you know, don't add lots of copper. If you add lots of copper, it will get worse. Right. What about zinc? After 7 days, nothing much will happen. Even with the high dosage. Meaning that at least for this plant, it can very well tolerate high zinc concentration. Yeah. Maybe sometimes people want to decide, can we grow this crop in this piece of land? And we know this land kind of have the accumulation of zinc and copper. We do not know whether the plant is going to tolerate well or not. So use this equipment, such as this one, to do the quick assessment, the capability of the plant. Yeah. So this plant can do very well with zinc excess. To plants that do not have this capability, extra zinc might cause toxicity symptoms. But this one kind of look happy. Look at this. Even after the treatment 3 or 7 days, it looks kind of the same. 60% use of the absorbed photons to do photochemistry, which is quite high because with rice sometimes I only got 30%. Yeah. I don't know for oil palm. Maybe it's even because oil palm is very prolific plant, right? Yeah. So how can you use with your crop? Maybe you want to see at different time frame after you have applied fertilizer. Right, you have applied a special fertilizer that has been, bombarded with marketing claims, and you want to see, is it going to do anything to the plants? Yeah, this will count, right? Okay, one. Yeah. So with LiCOR, the moment you do the 5 PS2, automatically you are going to get this reading as well. This is electron transport rate. The speed of the electron inside the photosystem too that you saw just now, right? The faster the the faster the electron that move, the more ATP that you're going to get, right? Okay, right. I think that's pretty much about it. Because the further slide is actually how to do it. Fluorescence measurement. Can you go to this slide? Next. Yeah. You want to do it? Is it done? When it's done, we can do this experiment. I think it's going to take a few more minutes. Yeah. So the good thing is we have been using the adapt that berperiod adalah cuma I think we need to shut the light kejap lagi masa nak buat ni. Not now. Laju tangan tu kan. Movie time. I don't think it matters much because this like one is far away. Maybe it's not the photosynthetically needed by the plant, right? Yeah. But my concern is because the window is transparent, I can see the yards sunshine that can actually reach here. When it reach here, the photons will quickly get into the whole reaction center. Fill in. Right. Okay. Right. So we wait for this to be done. And then we can take this. How about that group? Are you done? How many points left? Nampak macam glaring. Oh, kenapa slow? Dia laju ke? Tapi dah allow early matching. You should be quicker actually because you only set at 120. That one 180. Tak apa. Okay, macam ni. Once you are done with this, unclamp the leaf, shut the light immediately, close the file, open log file with a new fluorescence activity, baru nanti kita clamp dekat leaf ni. Light kena completely off tau, semua off. Yeah, off on the screen. Zero off. Maybe I can show you to do something. Can you go to fluorometry? That group can do that as well. Fluorometry. I need to shut the light. Maybe setting. Ibu macam tak ingat pula kan dia punya ni banyak sangat. Dia tak ada setting ke? I need to find the setting yang biasa tu. Mana lupa lah. Lagging. Okay. Ke sebab dia tengah buat ni. Oh dia dah. Oh sini dah pay, sini tak pay. Okay. Modulation on off. So kita offkan dulu. Kita offkan dulu. Yeah. Off. Attempting to mana ni pasal? Cable. Okay, so dah off kan? So the other group, go to fluorometry, go to setting, and then off this modulation thing. Okay. Yeah, yeah. Dark mode 500 Hz, light mode 250, averaging 100 volt. Okay, I think that's fine. Tengok multiphase ni? Tengok multiphase. Dia lagging ya? Okay. Right. Ini change it to 12,000. 12,000. Lagging? Tak apalah, buat pelan-pelan. Ni 12,000. Kan sebab dia tengah ada active auto program. Ini change to 12,000. Inilah saturating flash that I was talking about earlier. I think you can change it up to 16,000. So kita change to 12,000. 12. Yep. Done. Okay. Alright. Rectangle. That's fine. Induction. That's fine. Dark pulse. I think dark pulse ni tak buat apa kot. So that's fine. Custom. I'm finding the option 1 and 2 tu kat mana tu dah? That's it. Computation parameter. Not this one. This one. This is the result kejap lagi nak nampak. Event folder. Not one, compare event. Utilities. Itulah aku tak ingat. Program kot. Mana program? Pergi program. Program ni tengah buat benda ni. Mana ya? Ke dekat log setup? Login option. Ni fluorometer option ni. Fluorometer option ni. Ni. Make sure dia dekat nombor 1. And add rectangle untuk the other group. This group is fine. Dia dah betul. Yeah. Okay. Tengok dekat program. Is it done? Okay, it's done. Okay, tutup file ni. Lepas tu buka file baru untuk activity fluorescence. Dah tutup kan? Tutup lampu terus. Pergi dekat environment, tutup lampu sekali. 0. Set point, make it 0. Tak siap kejap. 50 tu betul ke dah siap? Sepatutnya kosong kot. Tapi dah kan? Sepatutnya light tu dah kosong lah kan? Tak apalah. Buka, make sure. Dia dah off terus. Okay. So I think tak apa, biar je sebab dia dah memang macam ni. Tutup file, buka file baru dalam folder yang sama, STROPI. So this new file will be dedicated for fluorescence activity. Ini dah boleh buka dah ni. And dah tutup lampu baru kita buka ni.
Yang ni belum siap.
Apa? Lagi ke?
Belum siap.
Belum siap lagi? Tak siap?
Ya,
Goyang sikit. Stress. Somebody unclamp the lift. Release the lift. Tutup balik. Lepas tu this plant pusingkan supaya the right lift facing this chamber. Turn the quad. Nanti dia koyak kan, nak tarik jauh-jauh tu. Kita tunggu dia orang siap sikit. Sikit lagi. Just make sure buat yang tadi tu ya. Lepas dah sudah tu make sure lampu tutup, baru unclamp. Tutup lampu semua, baru kita dark measurement. Kenapa ini laju sangat? Masih ada, tak tahu ada point yang missing. Tak cukup kan? Okay. Tadi fluoro option tu dah tukar jadi nombor 1. Yang dekat log setup. Dah. Okay. Sudah tak apa. If you want the data from both of this machine, do we have thumb drive yang bersih? Tak bersih. File mana yang kosong? Tidak. Yang mana? Kena close dulu. Tadi file tadi masih aktif. Close dulu baru dia create Excel file. Dia punya sistem macam tu. Okay, bila dah close, baru buka balik new file untuk activity fluorescence. Nanti dah sudah, you need to close the file. Otherwise, Excel tu tak macam macam group ni tadi. Dia pelik kenapa 0 bytes dia punya size. Cerah, matahari tu masuk di sini. Oh, boleh kot. Tak pun kalau apa ni, kalau ada plastik ni, somebody pegang kat sini supaya cahaya tu tak sampai ke sini. Kasih lebih. Boleh kot? Boleh lah kot. Cukup. Alright. Okay. Untuk group ni, you are ready kan? Maybe you can help kan untuk ni? Nampak kan ni tu? Meh, tolong Meh. Tunjuk. Ajar dia orang macam nak buka ni untuk clamp. Buka ni. Kalau dia basah, lap, baru clamp. Sekejap. Kenapa lampu ni menyala? Sebab aku tak tekan apa lagi. Pergi dekat dia dah off. Measurement beam dia. Tengok tu measurement. Kejap, mana setting fluorescence tadi? Tak ingat. Fluorometry. Setting. Measuring. On. Off kan sekejap. Off.
Yang moderate tu memang ikut setting ni lah. 500.
Kenapa dia on lah? Dia sepatutnya ni tak nyala kan? Nampak mula? Sekejap. Lampu kat atas tu? Kenapa aku nampak lampu? Perasaan macam Okey, tak apa. Dia dah off ni, okey lah. Dia dah okey. Okey, tolong tunjuk macam nak buka. So, buka tu perlahan-lahan. Tunjukkan kat kamera. Bawa ke sini. Amir, kau buat belah sini, Amir. Bagi nampak. Kita record so that nanti nak buat revision boleh tengok balik video ni.
YouTube kan?
You join with my class. I have banyak video class dalam tu. So buka. Sometimes when you wrap ni, daun tu berpeluh. Lap dulu. Okay, ingat at least you need to adapt half an hour. The best is overnight. Overnight ataupun 4 hours after sunset. If you want to do fill yang tak wrap. Okay, masuk. Okay. Sudah masuk tu kan? Okay. Sekarang ni pay attention kat sini. Ni sepatutnya tak tinggi tau. Sebab tak ada cahaya kan. Now turn on. Tengok jadi tak dalam sekitar 600 fluorescence level on. Ini fluorescence signals. However, dia tak cukup tinggi energy to do photochemistry. Yeah. The energy just enough to cause glowing in the dark, but not high enough to make sugar. Sikit je. So tak apa. So biarkan dia sekejap. Dia ada group tu dah ni ke? Dah clamp? Belum? Alright, okay. Pergi dekat fluorometry. Pergi dekat I think sekejap. Compare events. Competition. Sini competition. Okay. Okay, dah ready kan? Dah ready? File dah buka kan? Okay. Now kena cari mana button dia? Competition. Button flash kat mana? Kejap. Cari button flash kejap. Kejap bukan situ. Sebenarnya lock pun boleh juga. Kan? Tak apa, pergi balik dekat computation ni untuk tengok benda tu. Sekarang ni tak ada, ni really tak betul kan? Tadi main-main je. Okay, remember from the slide you learned earlier, it should be around 0.8 for LVFM. Tengok, pokok ni dapat tak? Tekan ni. Jadi tak? Ke dia tak jadi? Dia kena tekan multi flash juga. Ada? Tunggu kejap. Tengok ni, dia ubah tak? Apalah, dia tengah kejap, lock pending. Okay? Okay. Dapat tak? 0.8. So, this plant is healthy. Okay. That's why I said this number is highly conserved. If something wrong with this number, you know your plant is stressed due to the treatment or due to environmental condition. Tengok group sana. What did you get? FVFM? Pending? Macam lama sikit kan? Sabarlah. Oh, ya ke tu? Kenapa macam pelik je Formula 9? Tu terlebih sihat tu. Alright, okay, tak apa. Alright, now you have the data for LVFM. Now we want to get this data. So immediately after you have obtained LVFM, quickly turn the light back on. Environment, light tu letak 500, terus setkan 500. Dan ya. Nyala tak lampu? Tak tepi tu, nyala tak? Tak nyala. Kena on. Kena on. Okay. Alright. Okay. So ni kena tunggu sekejap lah, about 15-20 minit. 500 ni tak betul tak sebab kita tahu dia boleh build sampai 1500. Sekejap lagi, tengok measurement ni. Tengok measurements ni. Go to page 1. Okay. Alright. The moment this thing has start to become positive, boleh jadikan 1000. Okay. 1000. Lepas tu, maybe a bit more, 1200. Lepas tu baru bila kita tekan measurement again untuk dapatkan 5 PS2. We need to know from 80% of the captured light, how much actually go towards electron acceptor to do photochemistry. Right? Tunggu dia positif. Kalau dia positif dah boleh naik dah ke 1000. Macam dah positif? So the good practice is to increase this progressively. Jangan terus bagi 1000, nanti pokok terkejut. Right. Okay, good. Pokok ni agak responsif. Kan, responsif. What about the other group? Okay. Macam tipu je 0.99 tu.
Yang ni memang sihat. Lepas ni yang report tertutup kan dia bukan.
Sebab actually banyak saintis sedang cari pokok yang LVFM dia lebih 0.85. Sebab the whole planet LVFM 0.8 or 0.81, 0.82. If anything beyond 0.85, potentially dia ada genes, special genes yang membuatkan dia utilize photon habis-habisan. This is when you need to do the statistic. Kalau buat 2-3 pokok masih sama, I suggest keep this plant.
Satu paper lah setiap kan.
Maksimum dapat pun 0.84 macam tu. Ya. Dia tak boleh pergi lebih lah.
Tak pokok yang macam ni lagi dia makan dia.
Kan berseni. Pokok ni pun okey juga. Nampak dah 4 dah. Sekejap nampak naik kan. Remember that this morning it was so hard for you to increase ke 2 ke 3. Sekarang ni pokok dah bangun. Nampak dia cepat. Daripada kosong tu dah 4 dah. Sebab dia dah bangun. Mid-day depression has been eliminated. Ya, cukup tidur. Ya. Ya. Sebab tu afternoon nap is good. Rehat sekejap 20-30 minutes. Tahu ni. This is good. This is a good plant kalau macam ni. For a house plant, ni good lah, sangat good lah. I don't think dia stress sebab kalau dia stress, daun bawah ni dah banyak senescent, dia tak ada senescent sangat. So dia okey lah. Dan dia keluarkan primordium baru. Right. This is a sign dia happy. Nampak stomata dia? Tinggi lah. Tak apa. Kita tengok at 5 PS tu, tengok dia dapat berapa. Kalau itu pun dia dapat 0.9, nampak benar nipunya. Increase sikit lagi light, lagi 200 sebab dia dah sampai tinggi sangat ni. Bagi dia lagi light, 200 tambah lagi. Grup sana pun boleh buat kalau pokok tu dah mula like skyrocketing ke arah sana.
Dia nak LiCOR sebab pasal yang LiCOR tu kita.
Okay, I think we can tekan lock lagi a few minutes. So let's go back kepada fluorometry tu untuk tengok apa result graph tadi. Fluorometry. Lepas tu pergi ke ni. So kita adapt kan? Nilai adapt. Ini untuk 5S tu ni. Nanti once you press the lock, all this will be filled in. Semua ni. Ini tak adalah tidak pass. Ni different experiment. Boleh nak buat tapi janganlah nanti muka. Banyak dapat ni. ETR, electron transport rate. 5 CO2 pun dapat juga. 5 CO2 adalah kecekapan Kelvin cycle. Efficiency of Kelvin cycle. 5 PS2, efficiency of photosystem 2 of the thylakoid green pancake. 5 CO2 is the efficiency of the Kelvin cycle, the one that turning you saw earlier today. Yep. Dah berapa? Cuba tengok berapa reading? How about you? Dia dah stabilize ke? Your group ni macam dah stabilize ni. How do you know it's stabilized? Tengok dekat axis ni. 7.6 minus 6.2. Less than 2 or more than 2 units. Kalau less maksudnya pokok tu sebenarnya dah okey. Ya. Tadi kan besar kan benda ni. Tapi macam nak gitu. Ke dia gembira, dia tak pernah dapat cahaya yang betul seumur hidup. like Kenapa? Why?
Stable.
Dia maintain.
Maintain stable. Tapi dia punya saya rendah.
Ya. I think dia punya, tengok ya. Tengok CI for this one. That CI is 160, right? Maksudnya Rubisco dia banyak. Rubisco is the enzyme that used to fix CO2 into the system. Bila Rubisco tak banyak, even though you have lots of ingredient, nobody is around to make cake for you. CI dia tinggi. You have lots of ingredient. You have 10,000 eggs, but bakers only 2. This group got 10,000 eggs. Bakers ada 1,000.
Tak cukup orang lah.
Tak cukup orang. Tak cukup orang nak buat kerja. Tak cukup orang nak buat kerja. Tapi dia punya graph dah stable lah ni. Okay, dah stable. Let's sorry. Let's flash. Pergi dekat fluorescence and then kita tengok je depa. Boleh press dah. So tunggu kejap, dia saturating flash and everything. Dia buat benda ni sequential. Dia ada cara dekat dalam tu dia buat. So tengok berapa dia guna. It makes me wonder that group FVFM 99%, tapi photosynthesis 2 je. Macam mana tu? Okay. Alright. So nampak ada reading kat sini. So about 3% digunakan untuk actual photochemistry. Yeah. So ada banyak benda kenapa dia rendah? Mungkin sebab kita tak ada light adapt dia lebih lama. Or because this is shade plant, house plant. Kalau dia sun plant dekat luar, benda ni selalu memang akan tinggi. Tapi semua benda sihat. Nobody is negative. Fine. So electron transfer rate 18 tu maksudnya 18 micromole of electrons per second per meter pergerakan ni, speed dia. Yeah, MPQ is the non-photochemical quenching. This is usually the heat tadi nampak tu. Yep. What about your group? Less than 1? Berapa? 0 point?
0.007.
That's not even 1%. So maksudnya whatever tadi tu has been absorbed to the fullest, but almost none of it participate in photochemistry. It is evident because if you look at your assimilation, it's only 2. Look at your assimilation for this one. Pergi kat measurements, 9. What about you? 10 lah. 2. So, don't judge leaf by its appearance. Right. So just because it looks okay, tak koyak, nampak hijau, there is an underlying physiological biochemical story behind it. Okay? Okay. I think you kalau dah sudah, we can close the file, save the file. Macam mana nak bagi dia orang untuk dapat ni? I think tomorrow after we come back from the field, we look at macam mana nak interpret data that we have obtained today. Okay, so today we have data daripada light response curve, auto response curve dan juga FVFM and phi PS2. So tomorrow we can revise macam mana nak buat apa ni, interpretation. Pagi esok, bring that machine as well to the field so that you can learn macam mana nak buat on the go survey measurement. Kepit dapat data, kepit dapat data. Pak 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 pak. Ya. Yeah. Provided pokok to behave lah. Alright, okay. Dah close kan? Dah close, dah simpan. Nanti macam mana? Nak kopi ni tak apalah yang dia orang tu lah. Ada mana? Ada mana? Okay. Yang ni nanti transfer masuk dalam komputer lah. Sebab kita buka malam nanti kita buat short draft. Macam yang kau buat untuk minyak angin. Ush. Okay, boleh buka lampu boleh. Tak nampak buat kerja. Okay, alright. This group doing okay kan? Nombor dia kat belakang tu. Serial number dekat stiker, ada stiker kat situ. Okay, just for your quick attention, tadi we did a lot of fluorescence setting, right? Those setting actually ada kat dalam nota. Okay, modulation nak tukar berapa value, apa benda semua. This is the basic of it. I'm not saying that this is the best for oil palm. Okay, but for most C3 plants, this is acceptable. Okay. Okay, any questions up to this point? Banyak kan belajar pagi ni? Right. Banyak belajar hari ni. Are you open reaction center or close reaction center now? Half? Half. Ada yang buka, ada yang tutup. Okay, we are not going to do data interpretation today. Kita buat esok. However, since I'm around until tomorrow petang kan, if you have any plant related questions, it doesn't have to be plant physiology, as long as it's about plant science, you can throw at me later as well tomorrow. Maybe you have some experiment that you're not sure about how to deal with it, right? Okay. Sebab once I go back to UPM, bye-bye lah kan. So you have all the opportunity in the world to ask about plant science tomorrow. Okay, ada soalan ke for this session today? Is there any unclear, or I can ask question? Patutnya kita buat exam benda ni. Exam lah. Tengok my notes given to you like textbook, so colourful. Kan? If you quiz. Kalau kita buat quiz, boleh? Tak, ada hadiah tak? Okay, so I think just before we go back home, maybe I'll just make a short quiz, 20 minutes. Okay, maybe you want to divide yourself into 2 groups. So siapa yang habis dulu boleh bye-bye first. Siapa yang get the highest mark, you can go first. Hey, lecturer, what do you expect? This is how I torture all the students in the whole university. Okay, group first. Apa nama? Let's write down. Mana? Yeah. Okay. Boleh tak remove this? Macam mana nak remove this? Remove this just. This is getting in the way. Kena? Boleh. Siapa? Quiz open Chrome. Okay, ada 2 group. Group first apa nama? Carilah kawan yang agak-agak boleh membawa ke syurga. Apa nama group first? Neraka. Janganlah neraka. Apa group first? Foto? Group foto? Okay. Satu lagi group sintesis. Wah, okay. Satu lagi fluoro. Okay. Fluoro ke froyo? Fluoro. Okay. Okay, Mana marker banyak tu? Give me 1 minute. Oh, selesai. Okay, sikit je, tak banyak pun. Alright, okay. Dah lama kan tak pergi universiti? Let's get reminded what university lecture looks like. I just tortured my student last week. Okay. Lots of screaming involved. Okay. Siapa group foto? I don't know. Siapa? Oh, belah sini. Yang tengah belakang tu Hakim. Okay. I'll give marker for each of these. Nak warna hijau biru? Biru lah. Ambil hijau. Okay, hijau tu tak ada ink. Kejap. Ambil merah. Merah. Okay. So dia bukan nak balik dah. Kompat kan? Dah close reaction center. Okay. Some question when I ask siapa tahu terus tulis kat depan, whoever finish first and correct got the marks. Some question maybe you need to fill in the blanks or angkat tangan apa, just follow the instruction. Alright, it's a combination of various things. Oops, sorry. Okay. Tidak tanya soalan apa? Tak tahu. Okay. Okay. Name 3 properties of light that determine plant growth. Go. Ada 3. Boleh. Nak bawa apa opah grandma bawa. You want to bring ancestors along to the front? Go. Ini tempat tulis markah luar. Dalam yang kacau tempat tulis markah. Kuanti. Siapa siap dulu? Kejap. Quality duration. Okay, siapa siap dulu? Foto dulu. Okay. So it's all about speed ya. Okay lah. Foto 5, fluoro 4. Macam tu. Okay. Apa lagi? Tak boleh macam tu. Kena bersenam sikit, kena bangun lari. Okay, next question. Just answer whether it is soil or substrate. Okay. Belum lagi, kena tulis kat depan. Kena tulis. You need to run, grab the marker, run and write it. Siapa finish first, they got it. Alright, whether it is soil or substrate, write it. Okay. That substance is let lu. That substance is apa? Kejap, tadi bisa ingat. Dolomite. So ini siap, lepas tu ini substrate. Okay. So jawapannya? Betul ke substrate? What is dolomite? What is dolomite? Kalau nak apa tu betulkan dosa, siapa cepat dia dapat juga. I don't know, I'm asking. Are you sure? Apa dia? Ini tak tahu mana satu, substrate ke soil. Aduh. Tu sebenarnya dolomite substrate ke soil? Remember what I said today. Soil originating from a chunk of what? Rock. Dolomite is what?
Soil.
So it can become, sebenarnya it can become soil. Yeah. Because dolomite rock, weathering, breaking down, breaking up, everything, eventually dia jadi serbuk tanah. So the answer is okay. So nak bagi makan siapa? Sebenarnya dua salah kan? Okay lah, dia dapat lebih sikit sebab dia macam effort kan. Effort lebih bersenam. Okay. Apa lagi? Let lu. Okay. I want any chemist here?
Yes.
One chemist come next to me. Okay, I'm going to show him a word. He needs to stay silent. However, the rest of the body can go. You need to guess what that word is. Sabar, sabar. Kau tak boleh cakap. Dia tak boleh cakap, ni huruf C apa tak boleh. Dia akan cakap, ni bulat, besar. Ya, ya. Sabar, sabar. Oh, okey. Ini, bawah ni. Apa? By the way, ada dua perkataan. Bunyi sikit-sikit tak apa. Dua perkataan. Siapa cepat terus lari, tulis tau. Tulis tau, dua perkataan tu. Tak payah lari lah kot, just cakap je. If I dengar correctly tu. Kena letak tengah, orang ni apa nak tengok juga. Kenapa? Oh, okay, bias. I can see why it's bias. Kejap. Change. This is from group, sekejap. This is from group photo, right? Bring somebody from group fluoro untuk tengok perkataan. We change the word. Sekejap. Sabar. Ada banyak. Siapa tengok mana satu? Sekejap. So you from group? Fluoro. Not fluoro. Okay. Ni. Two words. Dua question. Tell your group.
My first name. First letter of my name, and then
Cakap sikit tak apa.
it's rain.
Dia sama tu. Two word kan?
Two letter.
Boleh je.
One letter.
Relative.
Sekejap, kira siapa yang dapat dulu? Tapi dia tulis full. Relative, apa tu? Apa ni? Okay. So siapa yang menang? Dia tulis dulu kan? Betul. Okay lah, bagi kat dia dulu. Tak, this is also correct. Okay lah, give 4.5. Alright. Okay. Sikit lagi. Sabar. Okay, I'll use this space. You need to fill in the blank dengan the words. Panjangnya. Tukarlah, panjang sangat. Sabar.
Calcium.
Oxygen.
Bukan.
Intensity tu.
Okay, siapa dapat dulu dia dapat lah kan? Satu, one word only. One word ini. Kat sini adalah huruf L. Hint, dia ada dalam one of the location in the green pancake. Tertinggal satu. Sekejap. Tak ada. Betul. Apa? Cepat. Tulis. Betul lah, ada kat pancake hijau? Betul. Dapat lagi.
Dia jatuh tempat lain tu.
Apa tu?
Dia jatuh tempat lain.
Kenapa tu lain?
Dia jatuh tempat lain tu.
Dia jawab tempat lain? So, tapi korang tak tulis pun. Okay.
Jawab soalan.
Okay lah, bagi 4. Alright. Okay, final question. Siapa dapat ni dapat 10 markah. Oh. Dia kira menang terus lah. Lepas tu semua orang boleh balik kan. Okay. Kejap. Okay, each group send one person macam tadi. Sebab this time, you cannot bunyi langsung but use the marker to draw. As you keep drawing, your group members guess apa benda perkataan tu. Siapa pandai melukis, okey lah. Sabar. Apa nak lagi?
Dia sebutkan dia tulis ni.
I saw tadi, sekejap. Mana tadi ni? Ni. So, this thing. 2 words. Ni. 2 words. Tak boleh cakap? You can rub the board if you need to rub the board. Tulis. Jawab je boleh lah. Two words. They can actually draw the structure and then you know it, terus tahu. Banyak sangat orang cakap. Apa kata? Siapa je tahu jawapan terus tulis. Your group tak nak address ke? Kau tak boleh cakap. Apa?
Tulis lagi.
Cepat. Tak boleh cakap. Draw je. Siapa kata slide tu? Who says that slide? Who says that slide? Cepat, cepat, cepat. Cepat.
Antara pigment kan?
Tahu tulis. Tak tulis?
Kena kompleks ah.
Dah? Dah? So, dapat apa? Antena kompleks. Betul lah. Apa dulu? Apa dulu? Tak boleh buka. Okay, this group menang. Yeay. Yeay. Right. Antenna complex. Antenna complex. Bukan antenna pigments, antenna complex. Apa beza antenna complex dan antenna pigments? Antenna complex. Oh, tak bunyi benda ni. Antenna pigments, all pigments other than chlorophyll A molecule. That special chlorophyll A molecule. Antenna complex is the island of everybody including chlorophyll A molecule tadi tu. The whole thing, the island. So, dapat. Okay? Alright, okay. So, that's all for today. So, thank you for participating. Okay lah, bagilah 9 lah. 9 ambil. Nak sangat. Okay. So, seronok student. Kan, rasa macam nak pecah jantung kan? Cepat. Kenapa dia tak tahu? Alright, okay, I think itu saja kot. What about the small group discussion? Okay, any question for today? Tak apa, tak nak hari ni pun, you can, mana tahu nanti mimpi baru tahu nak tanya apa. Like kan, why tomato yellow? You can ask tomorrow. Alright. Bear in mind, if you ask me statistic, ada probability I know about it tapi nak explain susah. You can ask juga lah kalau nak tanya. So, anything to help with your research. Okay? So, itu je lah kot. Right. Kalau ada your small group discussion that you want to do, boleh lepas ni lah kot. Okay? Alright? Okay? Happy? Alright, so thank you for coming. I'll see you tomorrow. Bye.